Okay, welcome to Subdivision History Day, SMI 2021. And this day consists of 3 different panels, and then each one of them will take approximately 50 minutes, and then between them we will have a 10 minutes breaks. In the first part will be early days of subdivision and before 1980s, and then I put the 3 people's pictures. They were the heroes, like original ideas like George Doram, Paul de Castelgio, and George Chaikin. And then, so I will share the first panel, and then the first speaker of the panel will be Malcolm Sabin, and then he will talk about the George Doram. And then next, oh, sorry about that, I didn't change this one. Like the Ron Goldman and Tony Rose will talk about Paul de Castelgio. And then, then Richard Risenfield, Ellen Cohen, and Jeff Lane, they talk about their work. And then George Chaikin, like in the emergence of subdivision curves. Then Story of the Cat, November 1978 papers, like classical papers. And then Do Sabin Subdivision will be presented by Malcolm Sabin. Then the Story of the Catmull Clark Subdivision will be presented by Ed Catmull. Now let me stop sharing my screen, and then Malcolm will take over, and then we will hear his story about the George Doram.
I'll have to find my screen first. Right. Okay. The story of Doram. Can you hear me?
Yes.
Yeah, good. Okay, right. The story of Doram. Come on up. It starts with this picture. Which I'm sorry,
Malcolm,
I'm sorry.
I don't think you share your screen yet. Like we cannot see the.
Where's the share screen clicker? Oh wait, it's all right. I saw it for a moment. Yeah, here we go. Where the heck's it gone? There should be 2.
Great.
You can see it. Okay, that's good. Right. The story of Doram starts that he was a lecturer in maths in the University of Lausanne just after the war. He had a colleague, probably in a different department, who had a student. And the student was sent on a work experience session over a long vac, presumably. And this was to a factory that made hammers. And he was sent to the department that made handles. How do I find it? So I've got to find the next picture. Oh, paint. Right. That should just give me next, shouldn't it?
Ergun, I'm not seeing a shared screen.
Yes, Malcolm, we don't see the shared screen. Actually,
well,
I know the Malcolm's picture. Just imagine some
screen.
kind of the.
Okay, there's my screen. Can you see it now?
No, we don't see it.
Well, it's up on my screen as being the thing I'm sharing.
Yes, that's right now that we are. Okay, this is the one. Yes.
Great. Okay. So all I've got to do is to get it so you can see it. Right. Doram had a colleague who had a student who was sent to a hammer factory, and he was sent to the place where they make handles. And that open. Doram 2. The way you make a hammer handle is to take a nice regular piece of wood, and it has to be the right color, of course. File open. Doram 3. And you mark out 1/3 and 2/3 along each edge. And then you take the saw, which is in the background, and you cut off those corners. If I hadn't lost the demonstration, you'd have seen these blue things move backwards with the cutting. Once you've done that, you find yourself with a, come on, a nice octagonal piece of wood. And again, you mark off 1/3 and 2/3, which makes a cross section with 16 sides. And of course, it's getting pretty close. So you just file those down and look at the next one. Open. Round 6. You file those down, and this leaves you with a shape with lots of sides. So you get the sandpaper out, and you've made a hammer handle. The colleague was quite interested in this when the student reported back at the beginning of the next term. And he has a look at the cross-sectional curve. You can't quite see it in this picture, but it looks pretty ugly. And he asked Durham, this curve, it looks a bit weird. And what's the equation? Durham had a think about this. He understood what had been said, and he came back with a clear answer. It hasn't got an equation. And then later, in 1956, he wrote the whole lot up. I've not yet read the 1956 paper, but I will do so before there's a proper version of this submitted for publication. Any questions? Yep, Joe?
Yeah, actually, I read the original paper. It's in French.
Yeah, me too.
I'm in Geneva right now, actually, close to where I used to live.
Right.
And so it is a very interesting proof about C2. Of course, it's only restricted to curves, right? You know the
Oh,
paper.
sure, yes. Yeah, this was only curves, but that you have to start somewhere. One, univariate things are much easier than bivariate.
It's a very interesting paper because he uses results in number theory.
Yeah.
Yeah, I haven't read it in because I don't work in subdivision anymore, in like 22 years. So I dug out his papers back then, and but it's exactly corner cutting, exactly what you guys were doing was to do in Sabin, right? It's doing exactly that.
We were,
This
well,
was
as I'll tell you later, we were really heavily influenced by Chaikin, over-influenced.
Yeah, of course, but this was way earlier, right? What this guy did. And he's done so many other things in mathematics, of course.
Yeah.
Duality, right, and all these things. Anyway, and it's absolutely great you're talking about this because it's actually on my webpage I have one of his early drawings from one of his papers, and it's basically corner cutting, and to prove C2, as we all know, is very hard even for curves.
Well, to some extent, this is C2 by accident, rather than
yes, that's very right.
And it's C2 because of the symmetry of the situation. You've essentially got your rectangle, which is just an affine transformation of a circle, and you get symmetry all the way through. So proving it isn't that useful because we really want to make shapes which are much more interesting than ellipses. Now, I suspect that the story got garbled, that what the people who were doing hammer handles all the time were actually doing was not using 1/3, 2/3, but using a varying ratio, which gives you an ellipse.
Yeah.
But they didn't tell the student that.
You don't really get a sphere, right? Because
this is 1D. The question is, do you get an ellipse?
Yeah, no, you get something that, but not a perfect circle.
Right.
Because you can't represent transcendental functions with a polynomial, right? So
no, but if you vary the ratios, So you start off at about 1/3.5 and 2.5/3.5 and vary those ratios so it's a non-stationary scheme, then you can get an ellipse, and you construct it by just drawing an ellipse, then taking the tangents that you want.
Yeah, but it's not a perfect ellipse.
Yes, it is then,
It is.
because you construct it explicitly.
Okay.
And maybe Durham's second paper talked about this. I will be reading it in the coming week when I'm off chemo.
Actually, the really cool thing about Durham is that he discovered fractals as well.
Oh, sure. Yeah.
Does anybody have a copy of the Durham paper you're talking about in French that they can post somewhere?
I have it.
I have a copy, and I think I know where to find it. It's in his collected works. De Boer references it in Corner Cutting Always Works. I had hoped to put up a page of references here, but it got lost. And that will give me a lead to try and find both of the papers.
Actually, I will stop
Malcolm, I
sharing
have a
such that we
question.
can see each other. Yes. Yes.
Malcolm, I have a question. You mentioned casually that Durham discovered fractals also. Can you say a little bit more about that? That's an interesting
That's
fact.
very interesting. Yes.
It wasn't me. I think it was Jos.
Just said
Ah,
that. Yeah.
yes,
Yeah,
okay, maybe
of
yes.
So if you change the ratios, how you cut the corners, right?
Mhm.
You can get, it's just, I don't know if he invented it, but it shows the relationship between smoothness. So if you choose the right ratios, you get B-splines, right?
Yes.
Quadratic B-spline.
Yeah, that was shaking.
Change the ratios, you can get all kind of interesting curves. And some of them, it's a bit older. I've looked in this really closely. I even had a web page when I worked for Alias. I don't think it exists anymore, but no, I read these papers and very interesting. So he, and exactly like Malcolm said, it comes from a very practical problem, how to chisel a hammer. It's so cool. And that led to all this advanced research. Anyway, Malcolm, it's your show.
No, it's Ergen's show.
Yeah, but
He's chairing, and we probably run out of time on me.
Okay.
It'll be next week
Let's go to
sometime.
the
I actually read these papers. I
Mhm.
happen to speak French. I grew up here in Geneva.
Mhm.
And but anyway, and there are also versions in English, I think.
Mhm.
But I created a webpage in English translating it. But it was in '97 or something when I worked on Subdivision. But that was when I worked for SGI, so it's probably gone. I never saved it.
Actually, so far this is great. I really wanted this kind of the interaction. So our next speakers are Ron Goldman and then Tony DeRose. They will talk about the De Castelja.
I'm not really here, so it's going to be Tony.
Okay. So
Oh, I was counting on you, Ron. My knowledge of de Casteljo's contributions are really kind of second or third hand. I first heard the name de Casteljo, I think from Gerald Farron and Wolfgang Bohm. And I believe in the context of when I was studying Gerald's work on triangular Bezier patches. And that work I just found just so beautiful, the way the geometry was explained. And I believe they were crediting de Casteljo with many of the basic ideas. And my understanding is that de Casteljo was working in the 60s and 70s primarily. And those with more historical information, please jump in here. But he was working at Citron at that time. And my understanding is that Citron wasn't allowing him to publish any of his work. And roughly the same time, Pierre Bezier was at Renault and was publishing. And so we know Bezier's name for many of the things that de Casteljo had invented and surpassed, but without attaching his name. So for me anyway, it was Gerald and Wolfgang who kind of began to expose de Casteljo's contributions. And I think Lyle Ramshaw knows a lot more about this history than I do. I wish Lyle were here, so I'm going to try to channel what I know through Lyle. And I thought maybe rather than providing any strong historical basis, which again, I have very little firsthand information of, I thought maybe I'd just give a personal account. And the personal account is only something I can do. So hopefully you'll find something interesting. And again, I'm sorry, I'm going to go a little bit past the 1980 in this personal history, but so again, I just love Gerald's work, and about the same time I met Lyle, and I was at Berkeley at the time, and Lyle was at DEC Research Center in Palo Alto, and we started a conversation. He was telling me about he was studying the de Boer algorithm, and he found this labeling of the points in the de Boer algorithm that was that sort of told him what to do next in the algorithm. He didn't have to remember anything, and I thought that was really cute, but didn't pay any particular attention to it. And a little while later, Lyle started circulating a document which became the blossoming tech report from CERC. And even so, the original tech report from Lyle appeared, I think, in the summer of '87, and he had kind of rediscovered polar forms, and even credited de Castelgio with having done so in the context of computer-aided design much earlier. And I don't have a date. Carl, do you happen to know when that might have been, when de Castelgio had discovered polar forms in the context of CAGD and I think also in the context of splines at that time? De Castelgio didn't publish anything, I think until '84 or something was the forms a pole paper, but I think his discoveries went back probably much earlier than that, maybe late '60s, early '70s. I think you're muted.
Are you muted? Yeah.
Been muted. I understood only via Lyle Armstrong. I think the Castelgio had a way of saying things that was not so clear to me, but I thought Lyle made it absolutely clear.
Uh-huh.
Actually, I'm unfortunate, I should say, Lyle could have said that he could not come. I wish he would be here. Yeah.
Maybe we could get him to record a session later, and we'll just cut it in.
Yeah,
because I think he's got the whole story in his head, and I would love to hear it. So Lyle's work on blossoming came out, and again, I thought, oh, this is really cute, but I honestly didn't get it, and it really took Ron to sort of beat me over the head and sort of force me to, you have to pay attention to this. And so Ron and I had a number of conversations, and I remember the conversation where it finally struck me the power of the approach that Lyle had rediscovered after de Castelgio, and that was the uniqueness of what Lyle called the blossom and what de Castelgio called the polar form. And so the uniqueness meant that you could write down any old formula you wanted, and as long as it was symmetric, multi-affine, and agreed on the diagonal with the polynomial you were after, that was the blossom. And then you could just start using blossom labels to basically derive all the algorithms you wanted just almost by inspection. It just took no work anymore. And I just found that so amazing. And still to this day, I sometimes do talks for people at Pixar and other places and talk about blossoming. And my tears come to my eyes still with how beautiful it is. And just everything comes out of blossom labels: subdivision, degree raising, dimension raising, not insertion. It's just all there and transparent. One story I will share is, I asked Lyle, where the term blossoming came from. What was his motivation for calling it that? And he said, well, I just felt like a polynomial is this complicated nonlinear thing, and it's sort of difficult to think about. But if you start pulling it apart, if you start opening the petals of the polynomial, you start really recognizing the structure of the petals, and the complexity just sort of reveals itself layer by layer. And so he sort of thought of that as a flower, and that's how the term blossoming came to his mind. Ron, do you want to add any color commentary to that story?
Yeah, a little revisionist history. You said I turned you on to blossoming, but actually you turned me on to blossoming. I didn't pay any attention to it until you told me about it, and I wasn't convinced. And I remember you're convincing me of the importance of blossoming.
Okay,
So,
well, maybe
we have
between the two.
different views of that.
Yeah.
A couple other things I wanted to mention. So Bezier had Bezier curves, but maybe surfaces too, but he didn't express it in terms of Bernstein polynomials. He had some other way of expressing it. It was Robin Forrest who actually wrote down the formulation in terms of Bernstein polynomials. And it could be for that reason that it's not so clear if you don't have Bernstein polynomials what the relation is to blossoming. It's the Bernstein polynomials that give you the relation to blossoming. One other comment I wanted to make, somebody said earlier about de Rham discovering fractals. Now, it turns out that de Casteljos algorithm is also related to fractals in the following way. If you use the Casteljos algorithm for any value between 0 and 1, say a half, then you iterate this algorithm, you'll get the Bezier curve. But now if you can place, let's do this in the plane. So you have control points in the XY plane, and you have some number between 0 and 1, and you apply the Casteljos algorithm, this will converge to the Bezier curve. But now suppose you take your control points to be complex numbers, and instead of subdividing, say, at a half, you subdivide it at some complex number, say a half plus a half I. Then what you'll get are fractals. In fact, if you subdivide it a half plus a half I, and you start, say, with a straight line, you'll get exactly the C curve. So you can generate any kind of fractal this way. You can generate Koch curve, for example, this way, and you'll get now fractals with control points. So these are the control points that come from Bezier curves, but they're the fractals that come from subdivision with complex numbers. And in fact, getting something smooth is kind of a rarity. Almost anything you do will give you a fractal. You have to do something very special to get something smooth. Right? You have to choose, you have to choose the de Casteljos algorithm special. You have to choose Lane-Wiesenfeld special. If you do anything slightly different, like some small complex number, or don't use a half, do something else, then what typically what you'll get is a fractal. You have to do something very, very strange or very precise to get something smooth. That's my experience.
But I throw in a point.
That's exactly
one point here, which
of the Rham. That's exactly his paper. There's a sweet spot where you get the right.
Sweet spot. I haven't read de Rham's paper, but I wouldn't be surprised if that's what he said.
It's very interesting how hard it is to prove that it's smooth, like with subdivision surfaces.
Because in general, it's not smooth. Again, you have to have the sweet spot.
Exactly. Yep.
Oh, this is so exciting. It's because I remember one of your paper. I didn't understand what complex part. I'm thinking about the similar problem now. Everything comes together. It's very nice. Thank you. So can we go further? Like we have 10 more minutes, and then let's go to the Chaikin, and then I believe Ellen, Rick, and Jeff will present them like Chaikins, and then plus the subdivision curves. And
maybe I should speak first. In 1974, Bob Barnhill in math and I launched a conference which became kind of historic. Some people refer to it as the launch of CAGD as an academic subject. At any rate, we invited, it was a small conference. We had pretty generous funding from O&R. And we invited luminaries, Bezier, Koons, Avon Malum, and various others. Most of the people didn't know each other and weren't aware of each other's work. So we thought it'd be interesting to bring them all in the room. Anyway, I don't remember, but somehow Chaikin came to our attention. He wasn't on our A list, but I think he contacted us and said he wanted to speak. So as I recall, maybe Ed and Jeff can confirm this, we gave him a spot to speak, and he put up this very enigmatic algorithm and said, voila, these are beautiful curves. And all these spline guys like me were kind of sitting there with their mouths open like, what the hell is this? And Chaikin was not a math type. I mean, he dabbled in math, but he was more artist, came more from the art community than the math community. And I think this, like Bezier curves, sort of arose from intuition. Anyway, after the conference, I thought about it and I had no idea what to think about it. So I started saying, well, you know, I'm supposed to be a curve and surface guy. Here are curves and I have no idea what these are. I was not aware of any previous subdivision work. So I was totally perplexed. And I began to look at it and try to figure out, well, if I could get a closed form formula for this, I'd be in business. And so I after screwing around for a bit, decided I could parameterize this curve by taking a binary expansion between 0 and 1. And if I went left with the construction, it would be a 0, and right would be a 1. This led to a monotonic onto parameterization of the curve. And from there, one could do some analysis and conclude that it led to quadratic splines. So that was it. I also want to mention a personal note here. Dave Huffman was visiting, the famous Dave Huffman of Huffman codes, switching theory stuff. And he was here on a sabbatical and he was actually visiting Tom Stockham. And Tom Stockham was reclusive. He was a tape expert during the Nixon tape time. So he was not to be seen. So Huffman was here and so we were two bachelors looking for company. So we got to know each other very well. And I wasn't sure whether this Chaikin stuff was worth pursuing, but David Hoffman encouraged it quite a bit. I showed him what I was doing, and he was then doing some geometry stuff as well. He was doing paper folding, and I trusted David Hoffman. His master's thesis and his PhD were both landmark works in completely different areas, Huffman coding and switching theory. So I trusted him to know what was worthwhile. So that's the background that I have to say. By the way, I touch subdivision. I don't think of myself as a subdivision guy, but I touch subdivision in 4 points in my life. One is Chaikin, one is Lane Riesenfeld, then the Oslo algorithm, and finally discrete B-splines, which have a profound connection to the loop scheme, which maybe Charles will talk about.
Discrete box splines.
Yeah, discrete box splines. And the latter two, well, the Oslo algorithm and discrete box splines were done with Tom Licka and Elaine Cohen.
Why doesn't Jeff go next?
Elaine suggests Jeff go to next.
Could I throw one thought in? That Robin Forrest tells us that you and he independently overnight after Chaikin's talk found out that it was a quadratic B-spline. And you've made it sound as if it was a much longer story.
You are muted. Rick,
Right?
we cannot hear you.
I must have gotten night, Malcolm,
Yeah,
because
yeah, I guess so.
I worked on it fairly hard for I mean, it was just nothing that I had encountered in my life before.
Robin was at the meeting.
Yeah, Robin was
told
at the
me.
meeting.
Yeah, Robin told me about it too.
I've forgotten that, and maybe Robin had figured it out, but I remember working on it for months and, you know, intermittently and showing Dave Hoffman my thoughts. And so that I don't know what to make of that, except that I don't remember it.
Elaine?
Why don't we let Jeff Lane go?
Okay, can you hear me?
Yes.
All right, that works. I'm getting pestered by my cat now, just walked in the room. Hopefully he doesn't jump on the table. So I kind of in sync with Rich there on Chaikin at Utah. I just had gotten to Utah, I don't know, 6 months or a year before that, graduate school. So I thought it'd be interesting to see, you know, what would be extensions of Chaikin to other B-splines, and starting to think about that. And other people that heard the talk were also looking at it. One guy that was looking at it in terms of extending it to B-splines was Ed Catmull. So Ed had made some progress and apparently had shown it to Rich. It's hard to remember it all. And Rich wanted me to go talk to Ed. So I did. I met Ed in the conference room. He showed me what he had. And what he had done is extended to subdivision of B-spline surfaces of basically any degree. And it was quite exciting. And but he also extended it to arbitrary topologies, where it could a vertex could be more than just degree 4 or less. It could be degree 3, degree 5, degree 6. And
Jeff, is your camera on?
No, and I don't know how to get it on. I did 3 trial runs of this yesterday, and it was on, and then today it wouldn't go on. So so it was pretty good what Ed had there, and I told Rich, I said, I think he's got it, and Rich's response is, well, we really need a closed form. You know, as Rich said, he found the closed form for Chaikin. He thinks for the surfaces we wanted a representation that was closed form. You can take a derivative, you can calculate the normal, and so I started at that time looking for closed forms of similar type of operations, and from there, I think it was really about you know, Ed was going to go on forward with that, and I was looking at something else, and but I had some inquiries about that same time about, you know, what was going on at Utah around Chaikin, and one was Malcolm Sabin, and another was Jim Clark, and I put in both at Ed, and you know, from the publication of the papers, looks like Jim Clark did follow up with Ed, and I don't know if Malcolm followed up with them or not, but they both came out with papers at about the same time. So that's kind of my history around Chaikin. Questions?
Yes.
Were you going to say something about Lane Riesenfeld?
Elaine and Riesenfeld?
Lane Riesenfeld.
Lane and Riesenfeld. Oh, our paper. So that was, I always thought subdivision was a good tool. So I thought, it's something you would use. You would put it in your libraries and things to work with B splines, and so the Lane Wiesenfeld paper is about looking at some of the uses you can use it for intersecting two surfaces. B splines were very difficult to intersect, but with subdivision you could find the edges easily. Roots of a polynomial, using subdivision as a sort of generalized Newton iteration technique, you could find the roots of polynomials. I implemented all these things. Now you're telling me to remember the paper. I didn't even read it for the meeting. Surface display, I did that later. That was actually a separate paper, but to me, subdivision was a great tool for working with polynomial surfaces and splines. And I don't know. So we did a bunch of experiments and implementations, and they worked.
So, Eden, do you want to add anything?
Sure, happy to. So I'll pick it up. Rich and I were on sabbatical, and at the time I wasn't working in geometry related stuff. I was
echoing. You got two microphones going.
I was doing more signal processing. Can you hear me? Okay.
Yes.
Yes.
Perfect.
We can hear
Okay.
you.
So I was doing more signal processing. At any rate, so we were off on sabbatical, and Rich and Jeff had finished Lane Wiesenfeld. Wasn't written up, wasn't published yet, but they'd finished all the work on it. And we went off to Norway. And Rich and I were then at a research institute, which is now SINTEF. Then it wasn't, but we went off to see this fellow at the University of Oslo who'd done some interesting math recommended by Larry Shoemaker. Rich dragged me along. I was working with Avon Malem, not doing geometry again. And we went off to meet with him because he felt, well, Rich was interested, how do we extend some of these ideas about subdivision to non-uniform cases? Because sometimes you want some areas more complex than others. So how do you deal with that? And Tom had done a thesis on something called discrete splines. So we went off and he thought, well, maybe we could use that. And it turns out that that was only for the uniform case. So one of the things we did was we sort of said, well, how about if we extend this to non-uniform cases? And we did, and ended up with the Oslo algorithms. So that sort of started my geometry career. Although before that, I have to admit, I dabbled in it, but only behind the scenes because we were young and tenured faculty. So you didn't mess with working with each other in those days. So, so that was that. And then after that, we said, well, how do we deal with cases where we don't want just tensor product things? So we started looking at probably all kinds of what were then called intrinsically multivariate splines. And these were new things that had arisen in math circles, and they were oddities that were really interesting mathematically. And we read paper after paper after paper after paper. And we finally happened upon these things called box splines. And from there, we sort of looked at that and thought, well, we can do something with that. And we discovered related things that we call discrete box splines, which gave us subdivision techniques of any sort that you wanted for box splines. And this was obviously only the case. Box splines can be triangles, which turned into one case of which Charles will talk about, but they can be much more complex things as well, because it all depends, they're projections of higher order boxes. So you can project in all sorts of ways in order to create odd shapes. And this algorithm gave a way to refine, subdivide, and evaluate cases of these things which could be very complex. And so that sort of delved into the intrinsic box blind subdivision. And I think that was, I'm already in the early 80s, so I'll quit.
Okay, now I'm time to go to 1978 papers. Maybe we can start with Malcolm. Then, so we are almost like 20 minutes, like the leftover, like it is 10 minutes per person. Yeah. Mhm. Or maybe Malcolm, you and Ed in the same time talk about it. Like you can free to use the time any way you want.
Well, I want to hear Ed's story, so.
Okay, so basically in the early 1970s, from the point of view of presenting images, everything was polygons. The work at Utah was to try to figure out how to display curve surfaces. So that was a task that I took on, and I came up with a way of subdividing the B-splines, and I recognized it was important to have a coordinate system on the B-spline, on the patch. The problem was that I had also made a movie with my hand, and I realized the technology in terms of stitching the patches together meant that you're going to have vertices with non-four-sided edges. So that was the problem I was dealing with. I was writing my dissertation at the time, and we had this conference. I was certainly influenced by what Chaikin said, but I was trying a large number of different schemes to solve this problem. And this particular problem was not related to my dissertation. It was just this really interesting side project. So what I did was I took the underlying math for the B-spline and I reverse engineered it into a set of rules for how you recombine the vertices and you iterate on a surface. And in order to prove that this worked, I ended up writing a paper. It's an 18-page paper using high school geometry to show why this worked. Now, I showed it to Rich, and Rich said, that's off to the side. Why don't you go back and finish writing your thesis? I did show it to Stephen Coons because he was on sabbatical there near the end of his career. He was very excited about it, and he was the one that came up with the term extraordinary points. Because after one iteration, all of the subsequent patches were four-sided, but the number of vertices that had non-four edges was now fixed. And then you can continue the iteration, but you always had something which an underlying point of view had a coordinate system on it. I graduated, then I went to Utah. When Jim Clark graduated, he joined me at New York Tech. And at New York Tech, I laid out this idea to him, and Jim Clark then implemented it, and we discovered we could make some arbitrary changes to the rules. We started to write the paper, and in the process of writing the paper, discovered that Daniel Dew and Malcolm Sabin had discovered something more in the quadratic form. And so having discovered that, the decision was we would publish the paper simultaneously. And meanwhile, Malcolm wrote up an analysis to prove points about the continuity at the extraordinary points. Then at that point, things kind of lay fallow as the field developed. And then the story on this particular thing leaps forward until Tony DeRose, which is years in the future. So for that particular time, that was my short summary of what I remember.
Malcolm, do you want to add?
Right, all I've got to do is find the share screen and then share screen. Let's try this. Right. Right, I've got two foils here. The first one is a big gripe. that I was reading a paper in CADJ. No,
Malcolm, you're not
CAGD.
sharing anything. Malcolm, you're not sharing anything.
Okay. Thank you for warning me. I've got to try and find out where the stuff is that I'm after. Sorry. I've got a picture of me here, and heck, where is the
Middle
share?
bottom.
Task Manager, Subdiv, Zoom, down at the
Share
bottom of
screen.
Zoom.
In the bottom, there is a things called share screen. If you move your mouse, it just appears. Otherwise, it is not visible.
That's great. I've been spending all day on this. Join the meeting, sign in. So I should be able to just shrink that. Shape Modeling International. Oh, it's just an email. Get rid of that. Zoom. Launch meeting, Zoom. I've got the meeting zoomed. Zoom Cloud Meeting. Zoom isn't giving me any option. It's saying to sign in. Shall I just sign in again?
So you were able to share before. If you do the same thing,
Yeah.
like you should be able to share.
Can you ever remember which things you hit?
There is a green button, Malcolm.
There ought to be a green button in the Zoom window.
It says,
There isn't.
yeah, it says
Below.
share screen.
At the bottom.
At the bottom.
Put
of
your
the
mouse
window.
at the bottom of the screen, the window, Zoom window. In the middle of it, there's a green
I've got the
button
Zoom
saying share
window and
screen.
it says sign in. So I'm going to sign
No,
in.
no. Where do you see everybody, Malcolm? Can you see people?
No,
Do you have?
no, that's probably the problem. Keep me signed in.
But you're signed in because we can hear you. You're part of it. So there's something.
Something is weird in Zoom and I don't understand it. Okay, right. Well, let me just tell you what I'm saying. If you can hear me,
Yes.
that's
we
it.
we can just listen to you. Yeah.
Right. Show video, it says. Yeah. Okay, right. The first thing is I've got a big gripe because I was reading a paper in CAGD just a few weeks ago. And this paper says, oh yes, Catmull-Clark did bicubics and Sabin did biquadratics. And I'm amazed that the referee let that through because Catmull-Clark describes both biquadratics and bicubics. The Sabin paper describes the analysis of all degrees. And so saying bicubics equals Catmull-Clark is absolutely false. And I'm really, really cross that the referee didn't pick this up. And there's basically no excuse for not reading the papers that you cite or for not picking it up as a referee. So if whoever wrote that is listening today, please don't do it again.
Well,
Right.
and in fact, what Catmull showed me when Rich sent me in there to see what he was doing was any degree. It could have been any degree. You know, of course, he was interested in bicubics for modeling, but it could have been any degree when he showed it to me.
Yeah, sure. That's the theory, but the paper itself does have reasonably long descriptions of both biquadratics and bicubics. I was reading them again yesterday, so.
Yeah, so your paper had the analysis, a very deep analysis, which was not in the paper that Jim and I wrote.
Oh, that's right. And interestingly, although those analyses have been improved, the more recent papers still have the same structure of exploiting the invariance as you refine, which is essentially eigenanalysis, and the invariance under rotational symmetry, which is the reason why you can partition it into separate frequency components. So both of those two concepts have actually persisted to this day in the analysis, although the analyses have been improved by other people. Right, let me move on. I have some confessions to make about the Do Sabin paper. The first one is I fixed up getting the two papers into one issue of the journal in consecutive pages. CAD Journal at that time was making the transition from being a magazine into a proper technical journal. And I was on good terms with the editor, who has unfortunately died since. But I sort of had a go with him and said, look, we've got these two papers. If you put them in the same issue in consecutive pages, then it'll have a lot more impact than if they appeared separately. And he saw the point of this. He was still a magazine editor and he wanted a scoop. So yes, we got them into one page, into one. And because I was clear in my own mind that describing a method was really should come first, I said, look, put the Catmull-Clark paper first. So it came in, there came an ascending page sequence of Catmull-Clark and then Do Sabin. Right. The second confession is that the Do Sabin paper does have a few lies in it. And I'll tell you what they were. The first one is that we talk about Fourier transforms, but we never used them. We used the idea from a book by Bachmann and Schmidt called N-gons, which in a sense is totally equivalent to Fourier transforms, but they never mentioned Fourier transforms either. In the proper version of this material, I will send the reference for Bachmann and Schmidt. It's a book called N-gons, and it's really, really weird, which is fun to read. The second confession is that we were totally focused on the surface equivalent of Chaikin until we saw the first draft of Catmull-Clark. And then we said, oh, well, our analysis techniques will work for this as well, won't they? Which was great. And the third is that the Do Sabin scheme is totally practically useless. I mean, it was a lovely thing to have in parallel with Catmull-Clark, but nobody uses the quadratic B-spline for representing any real objects. And because Do Sabin is the quadratic B-spline in the regular regions, that means that nobody's going to use it anyway. It was essentially a way of a good example for showing that things worked for the dual schemes as well as for the primal ones. And that's my confessions about it. Any comments?
Actually, I will say also you told me that how Ellen Cohen motivated you to work on this. Maybe you can tell that story. That was an interesting story. There may be other things like.
Well, Elaine has denied all knowledge of this, so she'll have to come back in and see if she remembers it now.
I have denied all memory of it.
And it's a long time ago. In the mid-70s, I think just before I went to Hungary, so it'd probably be 73, I had this idea that we could take Chaikin and push it into 3 dimensions. You can't see my screen, so it's I'm not going to show you the pictures. But I had the idea that, well, Chaikin just says take the middle of each edge and join up across the corners. So why don't we, in the surface context, take a new face in each old face and join up across the edges and join up across the corners, and we'll now get a new manifold, a new polyhedron, which we can apply time and time again, and it'll smooth out like Chaikin, won't it? And it was as simple an idea as that. And then I remember talking to Elaine, probably on a visit to British Aircraft Corporation. And it may have been walking back from lunch. So if the lunch was a good one, then I can understand not remembering. And I told Elaine this, and she came up with a beautiful question. What is the face that you're putting a new face in the middle of? And I'm sure it was Elaine, because that's exactly the kind of question she would ask. And I didn't know. But of course, I mean, I was brash and young in those days. So I said, oh, it doesn't matter, provided it lies inside the convex hull. And then, of course, I had to work on that. So I wrote, I first of all bought a book on, okay, the obvious answer was minimal surfaces, because they'll stay inside the convex hull. So I bought a book on minimal surfaces, and it didn't tell me how to compute points on them. So I wrote to the author and said, how do you compute these things? And he said, oh, you just solve a finite element problem. And of course, solving a finite element problem in every facet of an infinite regress is not going to be in any way practical at all. So I knew then that the only thing we could do was to make new points for the corners of the new face by some kind of linear combinations. And at that point, I was working with Daniel, who was a bright guy, and it just fell into shape. End of story.
How did you come to work with Daniel?
Robin Forrest comes into this story again. He had heard that Daniel was at Brunel University. He was working with a supervisor who knew nothing about what Daniel was working on. And Daniel, after 2.5 years of working on his PhD, had come to the conclusion that there was nothing left to do in CAD. Somehow he managed to talk to Robin, and Robin said, look, Brunel is close to Weybridge, where Malcolm's working. Talk to him. So I exposed this question of subdivision and how do we work out what it's doing at these extraordinary points. And Daniel picked it up, worked like a Trojan, and came up with his own scheme, which is actually the first scheme which was published. It was presented by me because Daniel didn't have a travel budget. It was presented by me at a conference. I think it was the one which became Eurographics. So I can call it Eurographics Naught. And I think it was in Bologna, but I haven't got any firm information about.
But Malcolm, your name was not on that paper, which has caused endless confusion with reviewers. I mean, I've had editors say, "Well, this doesn't make any sense. You're calling it the Due-Sabin scheme, but its only due is on the paper."
No. The scheme described there, I think it's a long time ago, described there was actually a rather poor quadratic, which when we'd done the analysis afterwards, we found we could do a much better one. So if you've got a copy of that paper, can you email it to me? Send me the PDF.
The Bologna paper you're talking about?
Yes.
I may have a 5th generation Xerox copy in a box somewhere with lots of staple holes in it, but I don't.
Well, look, if anybody else has one,
I can see if I can find it.
Yeah, because I don't think you could. Well, when you could see my screen, you could see my bookshelf behind, which is absolutely stuffed with old conference proceedings, and I couldn't find that particular conference at all. Maybe Daniel had the conference proceedings because he was the nominal author.
Actually, can I suggest something?
Tell a story maybe to jump in.
Mm-hmm.
So I contacted Due, and this was in 1998 or 99, 98, I think. And so I found his email, maybe through you, Malcolm. And he was someone working in finance, probably still is, in Hong Kong.
Well,
and he actually sent me his thesis. So I have it somewhere too.
That would be marvelous if we could share that.
Oh, you don't have it?
No.
Actually, that was one problem. I didn't have it.
I have it. I can scan it in.
Oh.
Not here because I'm stuck here because of COVID. But once I get back to Canada, when there's more sanity in the world, I can send it to you guys.
Yeah, put it on the to-do list, please.
Yeah, of course, I will send it to you, Malcolm.
Thank you.
I think I sent it to Tony, no?
Actually, can you send all of us? I will be happy to.
Yeah,
You may
Yes,
have.
please.
Toronto.
Yes, please. Yes, please.
Yeah, I have it back in Toronto somewhere. It's paper form. I can have it scanned in, no problem, or I can do it myself if you guys are interested.
You had got a lot of it.
I was learning about subdivision. That's why I was reading Durham. I knew nothing. That'll be the next session, I guess. I knew nothing about subdivision, so I was just reading everything, contacting people. I usually like to go to the sources, but anyway, I'm rambling.
So can I suggest something? We're supposed to have a 10 minutes break, but I think it's going so well. I think I will propose to go to the charts now, because it was like a naturally. It seems like a Charles Loop's term to explain the. Then we can go to the David and like I can just make it.
So you want me to go?
I will be happy. Yes.
Sure. So yeah, so my story starts early 1980s. I got into computer science because I wanted to do graphics. I mean, there was no, that was it for me. I understood that, computation was going to become a new form of a new visual medium. So I wanted to be involved in that. But there wasn't really any courses in computer graphics at the time, at least at my university, right? But Foley and Van Dam had just come out with their, I think, the first edition of their textbook, and they talk a lot about, the model for computer graphics I understood was a polyhedral mesh, a collection of faces and vertices and edges. And there was also these patches, right? They talked about Kuhn's patches and Bezier patches, B-spline patches, these patch things, but these ideas didn't really go together, right? You didn't, the mesh was C0 wasn't smooth, and you had these patches, but you couldn't really put these patches together in a smooth way. And then I was recruited out of my undergraduate university to go work for Evans and Sutherland in Salt Lake City. And Evans and Sutherland at that time was, the leading real-time graphics company in the world. And plus the University of Utah had the reputation from all the great work that, Ed and others had done in the 1970s. And so this seemed like, I want to do computer graphics, move to Salt Lake City. So while I was working at Evans and Sutherland, they offered, you could take courses at the university that Evans and Sutherland would pay for. So I got this catalog non-matriculated courses for students, and there was this one computer-aided geometric design, all about curves and surfaces. Oh, this sounded perfect. So I went to register, and it was went up to the desk and to register, and the woman said, "Oh, do you want the Monday, Wednesday, Friday version, or there's also a Tuesday, Thursday?" So I thought, oh well, Tuesday, Thursday, that's a lot less disruptive than Monday, Wednesday, Friday. I'll take the Tuesday, Thursday. Little did I know that was a pivotal decision, because that was the branch between either going to study with Rich and Elaine in the computer science department, or with Bob Barnhill and Gerald Farnell in the math department. And I had no idea, but just through that circumstance, I ended up in the math department with Gerald and Bob. So at that time, they were very interested in triangular surfaces, triangular Kuhn's patches, things like that, trying to put together these triangle surfaces. And also, as Elaine mentioned, box splines and refinement of splines. But over the regular setting, these were kind of the topics of the day. So I understood. So I wanted to solve this problem of the mesh with the patches, sort of make a smooth surface out of a finite collection of patches. It seemed like this would be a good sort of geometric modeling primitive, but it was a hard problem. Like, how do you stick these patches together? People were just publishing papers on like the geometric continuity rules between pairs of patches. But around an extraordinary vertex, that was harder. What do you do there? And I remember reading a survey paper, and there was a picture of, side by side in this survey paper of a picture of the Camel-Clark surface and a Du-Sabin surface. And I remember looking at those pictures and thinking, wow, that's kind of exactly what I'm trying to do. I mean, seems like they've done it. What's going on here? So I went to Gerald, who sadly is no longer with us. So I don't want to put words in his mouth, but more or less what he said was, and I think this has been said before and kind of characterizes the mathematical view. These surfaces, they don't have a parameterization. You can't take derivatives. They're the result of an algorithm, right? So they're not mathematically all that interesting. I don't think those are his exact words, but that was the impression that he gave me. And I kind of accepted this, like, okay, they're the result of an algorithm. There are other things that are a result of an algorithm. Like at the time, there were these fractal mountains where it was basically a 4-to-1 subdivision of triangles. You end up with these mountain shapes if you do the subdivision rule. So it didn't seem that far-fetched to me that, there were procedural ways of doing surfaces, and then there was kind of the true mathematical way of parameterizing a surface somehow. So around this same time, so anyway, I understood, box splines, the refinement rules of box splines. I wanted to do something with, irregular topologies. And I thought, well, studying and I understood, I saw, Malcolm's paper that he was referring to with the analysis of subdivision surfaces. And these were complicated by the fact that these were quadrilaterals. So there was two types of vertices incident on an extraordinary vertex. There was the direct edge neighbors, but there were also the diagonal neighbors. So there was this interplay of the diagonal and the direct edge neighbors happening that to me just kind of complicated the situation. So I realized that, triangulation, you don't have that. You only have one type of edge. You just have the direct neighbor edge. And I remember thinking, I want to have some model of a smooth triangle surface that I can kind of use to understand, all of the things that were going on. And I sort of occurred to me like, oh, well, I understand, how subdivision works. I understand these box spline subdivision rules. I can do the same thing for a particular triangular box spline. And it turns out it's even simpler, because instead of having to sort of change two, there's 3 rules in the Catmull-Clark surface, 2 of which I think are, well, there's 3 rules. And loop subdivision, there's only 2 rules, and only one of them that needs any sort of parameterization. So I had this idea to do it. I went off and implemented it with kind of the obvious solution for how to generalize the extraordinary vertex, which is to put the new vertex halfway between the vertex and then the average of the connected neighbors, put it halfway. So I implemented this, and it looked pretty good. I was pleased, but at the valence 3 vertex, there was a sharp point. It was pointy. It was obviously not smooth there. It was like a sort of a tip of a cone. And I had seen Malcolm's paper on the analysis, and to be honest with you, Malcolm, I really didn't understand the paper all that well. You mentioned Fourier transform in the paper, and I think that was probably got me off on a particular path, because then I started looking at Fourier transforms, studied discrete Fourier transforms, did all my analysis kind of in that framework, actually came up with sort of the correct solution for, getting the right spectral analysis within the degrees of freedom, in a kind of a crude way, but it sort of worked out. And around that same time, Tony DeRose came to, I met him twice in the same day. He visited Salt Lake City, he visited the University of Utah, he visited Evans and Sutherland. I showed him what I was working on, and at that point I was very hooked on research. Thought this is really cool. I want to go back to graduate school, focus on research full time. I had met Tony, so then I went to Washington, and Tony had just written a thesis all about kind of connecting manifolds with patches. How do you sort of build these collections of, how do you build a spline surface out of a bunch of patches? He provided the whole theoretical framework in his thesis. And this was a problem I was interested in, so it seemed like this would be a natural thing. Let's get together, go to graduate school, and work on this problem. So eventually, in my PhD thesis, I actually did solve the problem that I was originally went out to solve, which was, a single patch per opening in the mesh that's smooth, but it's like nobody cares, because subdivision won the day. And I think the reason subdivision won the day is because just the simplicity of it, right? The rules are so simple that, it just doesn't take any analysis. It's simple. People can implement it easily and get nice looking surfaces. It's no complicated equations. And I think this is the reason why subdivision surfaces have won the day. It's not that we can't build these spline surfaces out of patches. We can, and we can probably do them with arbitrary orders of continuity. But the complexity of doing that is just so great that subdivision just is the natural choice.
Actually, this is a great point, because that was something I was wondering, because the Tony DeRose went to the Pixar, and then you were working on the one direction, and then you sort of split, and then
Tony and I. So Tony was at,
maybe Tony
the University of Washington.
Say something about
and
that.
then, but the only thing I wanted to add was that Tony and I worked together. Then I think we were we studied subdivision back in those days. I think it wasn't clear to us that subdivision was the answer. I think we felt that subdivision refinement was a really interesting and wonderful property, but maybe there was a scheme out there that you could get both sort of finite numbers of polynomials and refinement. Back in those days, we just didn't know. I think, 20, 30 years later, it's clear that that's not really going to work out, that the refinement is the thing. But then, Tony and I hooked up many, many, many years later, actually, to make some more contributions to subdivision. I'm not sure if we'll ever get to that in this conference, but while he was at Pixar, we worked on something called Open Subdiv to put subdivision surfaces into hardware, or to use the graphics hardware to implement subdivision surfaces, which I guess is still probably used today.
Actually, this is the next step, probably.
Well, I know that's the session is like going mainstream, but this was much later.
But I think we are going in that direction. Like Tony went to the Pixar, and then Ed was already in Pixar. How you moved to Subdivision? Actually, I think Charles very elegantly explained.
Well, I think. Well, I'm not sure if Tony's still on this call, but yeah,
he's like
okay. Yeah, so like I said, I wasn't really looking to work on subdivision. I was much more interested in sort of splines over irregular splines.
Yes.
And subdivision just happened to be a tool I thought would be useful for studying this problem. And then once I had developed the algorithm, I recognized like, there's a lot of triangulations in graphics and scientific computing. Perhaps people would want to have an algorithm that would allow them to smooth this. Maybe this is something worth doing in its own right, but it really wasn't the thing that I was trying to do.
I don't know, Tony, do you want to add something? Like, I think that's very interesting direction right now.
Sure. I don't know if this is the right point, but Charles's description of his path, my path into subdivision was kind of similar. As Charles mentioned, I clearly remember the day I visited you and saw your demo of your master's thesis, and it was probably 4 or 5 years before that when I started working with Brian Barsky, and he had beta splines and geometric continuity of curves, and so from right from the beginning, I was interested in generalizing B splines to arbitrary topology, arbitrary degree, knot insertion. I wanted closed form. I wanted the whole thing, and so working with you and Steve Mann and other grad students at Washington, started to try to figure out how to patch things together, and because that seemed like
and I think subdivision offered a great model, right? But we just didn't. I don't think we realized that this was the answer, or at least this was the answer that was going to emerge years later and sort of dominate the field. I think we just didn't. It was an interesting tool, but perhaps there was something better that we could develop.
Yeah. So right, it seemed like explicit patching was a good step toward a more general theory, but
right.
But even explicit patching turned out to be really difficult, and then several other, like I think Jorgen Peters, started realizing that, if you could separate extraordinary points, then the patching schemes would get a little bit simpler. And the best way to separate extraordinary points was by subdividing a couple of times, maybe just once or twice. And so by that time, it seemed like, well, gosh, if I have to implement subdivision and patching, why bother with patching? Why not just use subdivision all the way down? And so that, kind of recognition led to the work I did with, Hughes Hoppe on surface reconstruction, where we're fitting subdivision surfaces to data, and that led to creasing. So this started to really seem interesting.
Can I jump in?
I just want to. Well, let me just make one comment about your work with Hughes. Though, I just want to say that. So I had written.
Josh also wants to say something about the. Maybe.
No, is it my turn to sort of tell my story? Because this sort of contradicts what I.
I was just going to add a comment to. Go ahead, Yos.
No, so is it my turn to give my little speech, or? I just want to comment that, I came to Subdivision in 1997, came to Seattle, wanted to live there, and they were working on Subdivision. They were working on this SpeedForm project, and they had this. They told me, we want your help for this crazy technology that's really weird. It's like fractals. It's called Subdivision. Okay, so I knew nothing about Subdivision. I knew about B-splines, other stuff, fluid dynamics and stuff. And so they started to explain it to me. Okay, so there's B-splines almost everywhere. And then at the extraordinary points, you can do eigenanalysis. Okay. All the stuff I know, just math. And then I was reading papers, and he said, everybody focused only on the first eigenbasis functions. And I was working on a presentation for Eurographics on something completely not related, about modal analysis to model tree motion. And I'm like, why don't we use all the eigenvalues, all the eigenfunctions? Of course, inspired by previous work. What's his name? Sorry, the work by you, Tony, was Cass
And Mark Halstead. Yeah.
Yeah, exactly. Great paper, by the way. And so, and back then it's like you cannot evaluate subdivision surfaces like parametric surfaces. And I came in an office that was bought by Alias Wavefront at the time. And they created this library for NURBS. So they had all the tools for NURB surfaces, curve on surfaces, intersections, booleans. And so I gave it some thought, and I said, well, you can evaluate subdivision surfaces, and they're just like parametric surfaces. So like, okay, because they had a whole list of problems. How can we implement this? But by having the evaluation, they're able to solve all these problems all of a sudden. So I was able to work on other stuff. Okay, this project didn't work out because if you have booleans, their workflow was SpeedFlow at Alias Wavefront was a new project. And so if you take booleans, you get bad meshes, and therefore you get bad subdivision surfaces. Okay, because there's an assumption that you have B-splines almost everywhere. So that didn't work out, but there was a lot of technology that we developed, and that went into Maya. Okay, so Maya now had subdivision surfaces. Long story, they were using hierarchies, which I always thought was a mistake. But anyway, it became a big success. People were able to use subdivision surfaces in Maya. And that was, and I've done some other stuff with Charles as well. We worked on quad triangle subdivision. Another thing that Malcolm mentioned, you can construct subdivision surfaces that generalize B-splines of any degree by taking duals. And you can see, in having a correction, you can improve the smoothness of surface. So that's pretty much a summary. My last paper on subdivision was to combine my fluid work with subdivision to simulate fluids on any surfaces. That was in 2003. Since then, except for working with patterns and stuff like that, I haven't done much. And I want to take this occasion to thank Ergun for inviting me here to speak. Thank you.
Actually, so I messed up a little bit because I was thinking to have the 3 different panels. We sort of merged them, but the way it goes right now, probably I think it's naturally emerges structure. And what I'm wondering, like the Tony DeRose went to the Pixar, then in Pixar, eventually we had a movie, and then in the same paper and then young Pinkawa is here, at Katmull is here. I don't know what resulted to turn it to use it in the movie, like, because also that's a big decision.
Well, just one comment here is that I knew that Tony had figured out a way to add creasing with his work at University of Washington.
Oh, yeah.
So basically, lured Tony away from his position there to come to Pixar, and we come out with our first film, and we wanted to restart making short films, which we stopped doing when we were making Toy Story. And Jan Pinkava had a unique idea, so Tony joined us, and at the same time we had David Baroff and I'm forgetting the other person from CMU.
Oh, yeah.
And working on simulation. So we had this rather unique idea with a new way of generating surfaces that Tony brought in and implemented for the short, as well as cloth simulation in that short. It's extremely influential short, and the surface technology was so unique that they started to use it in the feature film that we were in the middle of making, which was A Bug's Life. So people recognized right away that, okay, now we had a new and better way of creating surfaces. Anyway, Tony, that's the...
Okay.
Yeah, Jan, do you want to talk about some of the creative direction for Jerry's game? Because the creative direction really led to a lot of kind of soul searching and deep technology development. So
actually,
yes,
Jan Pinkau
I'll be
is
very
here.
happy.
Yeah. Do you want to?
Everyone hear me okay?
Yes.
Yeah, great. Ergun, thank you again for inviting me also. I have to tell everyone I'm a sort of interloper here. I am somewhat interdisciplinary, but I'm really an arty-farty guy. And even though I have a comp sci degree and a robotics PhD, I was really able to do the Jerry's game short at Pixar because I'm not afraid of people who aren't afraid of math, a sort of second order thing. And so it was great to work with Tony and Michael Cass on these two directions of the surfaces and the cloth simulation. And I'm here today, I guess, also because it was some years ago I spoke at Texas A&M and was lucky enough to meet Fred Park. I should say I was inspired to get into computer graphics from the very beginning because of a TV special in the UK about the history of computer graphics that showed, amongst other things, Ed and Fred's Computer Animated Hand, classic, first ever short film, which in some ways led to the fact that I was continually doing hands and faces in all the work I did practically in computers. So I was directing commercials at Pixar, and since arriving, inspired by the work of John Lasseter, was trying to do short films in between the commercial work we did. And when Ed wanted to restart the shorts project, as he said, I was ready and waiting with drawfuls of ideas. And Ed said, as long as you have a good story, which is the key thing, a good story. And he was the first thing he said. And as long as it has a human character, because that's the technology and the capability we want to push, then you can perhaps make a short film. And I had many, many ideas and no human characters at all in any of them. But I said yes, and then tried to figure out how we could make a short with a human character, which I knew from my slim tech understanding would be very, very difficult given the state of the art at the time. And so I set myself the task of creating a story with just one character in it, because just getting one done would be hard enough. And so that was the framework for how can we make a story with just one character, which is usually a bad idea because you want conflict in a story, something happening between at least two characters. And so the idea came up because of my maternal grandfather, who used to play solitaire chess, of having this chess game happen in the park. So an old man, and it was all going to be close-ups. It was all going to be a show with headshots, as we say, that required expression, acting, tremendous amounts of subtlety in the animation, and therefore a whole other level of doing surfaces. But I came to it really with a sensibility of sculpting and a tradition in puppetry from my old country of Czechoslovakia, where I was born. And to begin with, did a lot of art development. Here's a little sculpture I did of Jerry, the very first piece of three-dimensional work on the project, which is just expressive and just to get into the mood of things. And if I can share my screen, I'll have a go. Show some art. This is an arty interlude, non-technical. Can you see this?
Yes.
Okay, so here we are, Jerry. Some of the development work, the first ever stories, sketches, this sort of thing was the sort of artistic inspiration. How do we render an old man, and the gestures and styles of what's going on? Something that can have something as expressive as these sort of sketches in a surface. it had been impossible up to that point. We ended up going through sculpture, working with, I remember Jerome Ranft, the sculptor at Pixar, developing a look which was very much a stylized puppet-like look, very much inspired by my animation hero Jiří Trnka from my childhood in the Czech Republic or Czechoslovakia. And I remember at the time it seemed to be a point of debate among many of the technical folk at Pixar about what sort of human characters we would have, because the characters in Toy Story were the least successful, the human characters. They were the hardest things to do at the time. And what was the right direction to go in? And the clear thing was this stylized puppetry style. And it took a lot of communication, a lot of thinking about how these forms should move, a lot of design and drawing. And ultimately, it was Tony's work with creases. Creases were mentioned. They were very important. It was about getting these very exact transitions between edges and smooth surfaces, so that we could get a shape that worked. By the way, I don't know anything about Oslo algorithms. What I think Oslo is most important to me for is the Vigeland Sculpture Park. If you've ever never been to the Frogner Park in Oslo, I highly recommend it. I think he was the greatest figurative sculptor in the 20th century. Extraordinary work. You must go if you haven't been.
It's an amazing park.
It is absolutely amazing, just hugely inspiring. And I was a teenager when I first came across it. It blew my mind and inspired me to do what I was going on to do. So one character, I remember it was the job of a young man called Paul Akeley to do the rigging for this face, and to work closely with Tony on making it move. And to me at the time, this was the hardest thing. Creating a form was one thing, but making it move in a coherent, reasonable way, in a way that one would expect intuitively, in a way that the audience would accept as plausible, was the most difficult thing. Malcolm asked me earlier how many control points were in Jerry's face. I used to know, and I will answer that question for you, Malcolm, but it is hundreds, and they were all hierarchically structured to create the controls the animators could use. And it was by far and away the most complex rigged character at Pixar at the time. One of the stories I have of working with Jerome the sculptor is on the hand. Here is Jerry's hand, which I sculpted a version of that he put together. And I remember Jerome was bending under the weight of my persnickety notes, having too precious an eye for every little detail. And it came to the point where he said, here's the tool, here's the sculpting tool, you do it, which I always thought was a sign of his intelligence and production experience, not wanting to be bowed by constant note giving and allowing someone like me, who happened to be terribly nervous about shape and structure, to sort of directly sculpt it. And we ended up, it was all about faces and hands. That was the show. The rest was the cloth, which is a whole other story. And there's a famous story about Steve Jobs wanting to involve Giorgio Armani, but that's for another time. It's really just about acting. Here are some early storyboards of the second version of the show.
Did you draw the storyboards or somebody else?
Yes, I drew the storyboards.
Oh, that's yours. Okay, that's impressive.
Yeah, this was a tremendous opportunity for someone like me to be working with the technical skill and the math background that was there, with these brilliant people, both on the art and the tech side, and to be so supported in making a film that was essentially very complex and hard to do at the time. It took us about a year, I believe, Tony, is that right? From beginning to end.
we were a year in pre-production and then another
Yeah.
year in production.
Right. So it was quite demanding for the 3.5 minutes that the film eventually took. But there was nothing but support from everybody. Great teamwork and attempting to just make it work, because it was Ed's mandate really that ultimately there are only so many toys and bugs and other things that you can tell stories about. You have to be able to tell stories with human characters. So this was something that was strategically of tremendous importance for Pixar. What else can I tell you? This was, it did end up with getting us another shape and surface like this one, and that led to many opportunities. I do remember that one of the challenges goes back to the question of creases and the actual control mesh that produced the smooth surface being slightly different in space. I remember when Paul was looking at the early images of Jerry, it seemed to me that the nose wasn't big enough. There's a famous story about the great English sculptor Henry Moore, who, when having his maquettes enlarged to enormous size by his assistants, apparently had an outrageously sophisticated eye at tiny details, where he insisted that his assistants had actually, in a monumental size sculpture, changed the curve of one part of it by a few millimeters. And no one thought this was possible, and that this was just some sort of delusion. But after careful measurement, it turned out to be true. He just had a terrific eye for the exactitude of form, entirely aesthetically. I suffer from this a little bit in some way, and it was a long part of our conversation in developing the look of Jerry's game to ensure that the curves were right and the angles were right and the creases were right. And so it was about just working it until it looked good, and everyone was up for the challenge, and Tony was up for making it work. I don't know what you'd like to say, Tony, about the process.
Yeah, I've got a copy of the hand here as well. And so Paul digitized and rigged the head, and I volunteered to digitize and rig the hand. And I don't know if you can see in this in the sculpture, but it's kind of partially polygonal. There are some fairly flat areas, and then some areas that are sort of really tight radius of curvature. And when I started to try to model that with subdivision surfaces, Catmull-Clark surfaces, I started by putting lots of control points close together along some of those slightly rounded edges. And it was at that point that I realized, gee, if we had not completely sharp, but sort of semi-sharp creases, that we could get just the kind of radius of curvature control that Jan was after. And so that was kind of the genesis of the semi-sharp work. Then we also had to figure out how to texture them and how to animate them and how to simulate subdivision surfaces. So that was just a really fun period of invention and creativity, and having Jan in there to make everything look beautiful around a great story was really rewarding. So great project.
I think it came time to go to the theoretical contribution. Like I think we can treat them in the same group. Like, let me just so Niradin, and then David Levine, Ulrich Rafe, and Jörg Peters, and then maybe you can just start to talk about them. We can slowly go to the 2000s. Do I make sense?
I think I will start.
Yes.
My name is Levin, and since 19 85, Nira and me are working on subdivision. Also other things, but mainly on subdivision. And I want to tell you how it started. Before 85, we were working on radial basis functions, on theory of radial basis functions. And in 1985, I was also working on a reconstruction of 3D objects from cross sections. And I needed a tool for approximating curves. I had no idea about the work that has been done in subdivision. And I knew some splines, but not even heard of subdivision. So I looked for a simple rule for inserting a point in the middle between two other points. Of course, if you just use 2 points, you get piecewise linear. So I was looking for 4 points. And the only 4-point rule which makes sense and which is exact for constants and for linear is the 4-point rule which appears in the 4-point scheme. And there is no other rule. So the rule is there. And the new thing for me was to introduce refinement. So I wanted to make some tests. I knew programming in Fortran, but in Fortran, to draw curves, it's not very simple. So I asked my son, Adi, he was then 13, and he already mastered BASIC on a Apple compatible PC. So I asked Adi to program this scheme, and he did it, and in a few minutes I could see the curves, and they were very interesting, just changing the parameter, going from nice curves to like fractals, very nice curves. So I have shown it to Niradin, and since I didn't know anything about subdivision, I told her that this is going to be the new hot subject. I didn't know that it's not so hot anymore, but for me it was new. And at that time also John Gregory, he came to visit us in Tel Aviv, and we were sitting together trying to understand these curves and to prove convergence and smoothness. And this was the start of the interpolatory subdivisions, which are not were not used before as much as I know. So I will let now Nira continue and tell us about the continuation of the story.
Okay. You hear me?
Yes.
Okay. I read again our paper on the 4-point scheme, and I was surprised to see how much we did as a first step, because all what we did later was just generalizing it to more to other type of schemes, but all the ingredients were already there. So we really did a nice analysis of the 4-point scheme, and from that we went on. The next step was to find a subdivision scheme for surfaces. And we chose triangulation because any set of points can be triangulated. I remember that this was the argument. And we started together with John Gregory. It was in Brunel to come up with some scheme for refining triangles. And we did things that were similar to the 4-point scheme. And then David and me, we drove in a bus from London to Cambridge. We were going to visit Powell. And I remember we were sitting in the bus and finding that the scheme that we designed with John was not good because it didn't satisfy a certain necessary condition. By that time, we knew that we knew how to get necessary condition. And it won't converge. So we played with it until it satisfied the necessary condition and didn't violate any necessary conditions that we knew about. And we came up with a butterfly scheme. You know, we call it butterfly because the insertion rule, when you draw it, looks like when you draw the points of the taking part in the insertion rule of a point on an edge, it looks like a butterfly. And then, of course, we had to enlarge the tools in order to analyze this scheme. And I think our tools, and I think it was our tools were Z-transform and or generating function in another. Z-transform is more engineering type, mathematical notions. The mathematical notion is the generating function, and we use the symbol that was defined by then. Also, Charlie Micheli and Prouch were working on subdivision. So they came up with this idea of the mask and the symbol, and we used it, and we got an algebraic way how to check if a scheme is convergent or not, and even for surface schemes. So this was one thing, and the butterfly scheme, I think, is a very popular scheme. At least we got the most it was cited more than the 4-point scheme. It is very popular. So I want to tell on something. I am looking at my paper. I wrote on the paper what I want to talk about. Okay, I want to speak about another point. We already knew a lot. At those years, really, the 4-point scheme was published in '87, and the butterfly scheme very soon after. But then subdivision, I remember Malcolm did a graph, how many papers per year are published about subdivision. And it was a very exponential growing graph. In this year, late 80s and beginning of the 90s, this was a huge subject. So there was one thing about, we did a lot about interpolatory scheme. We wanted to understand them because they were so different from scheme for splines. Because for schemes for splines on regular grids, you know what is the limit. And then you don't have to worry about convergence. But here we had just a finite set of coefficients which have to determine the whole process. And this was very interesting to see that how much we can get from this small number of coefficients, what is called the mask of the scheme. And then it was very well known among subdivision people that look at the spline scheme for an example, that if you want to get higher smoothness, you have to take a bigger support of the mask. And the B-spline type function that you get in the limit has support as the mask. And when we write subdivision, we say that you get a high smoothness and you get a locality. The curves are defined by a local number of, at a point, by finite small number of coefficients, of initial points, of control points. And but then we knew that in order to increase the smoothness, we have to take a bigger support. So in order to increase smoothness, we lose the locality of the scheme. And we looked for a way how to solve this limitation. So we wanted to find a locally supported function on a small support that is very smooth. And then we found a way. If you take at refinement level 1, the mask of the B-spline of degree 1, at level 2, the mask of degree 2, at level 3, the mask of degree 3, and so on and so forth, you get a compactly supported function on 0, 2, which is C infinity. It has infinite number of smooth derivatives. And so we went into this whole big topic of non-stationary subdivision. And there's a lot still to study. And in fact, we wrote, I don't remember at what year, it was beginning of the 2000, that we wrote an acta numerica review paper on subdivision, where we start from this idea of non-stationary scheme, that in each refinement level you use a different rule, and in the talk of Malcolm, there was a question whether you can get really an ellipse, you can get really all you can get all trigonometric function. In fact, it is somehow related to exponential splines and not to polynomial splines. Okay, here I will stop, because if I will continue, I have a lot to tell about. So I will stop here.
Sorry, can we hear now? Jörg and Uli, like.
Hello.
Hi.
Hello. So yeah, it's fantastic to see all the people who helped with the bringing subdivision to the masses, so to say. It's Gary's game was an inspiration, and it's just fantastic. And if I listened to Jan properly, what subdivision did for you was to remove distractions. You could actually just model your meshes and things would work out in the back end, especially when there were these semi-fixed creases. So this is certainly what made subdivision fly. But there was always this ping pong game, as we heard in the very beginning, this ping pong game between the theory and the usage. And the usage is fantastic. The theory was typically lagging behind a little bit, but each time we learned a little more about the theory, we came up with new tweaks to existing good solutions. So we had the RAM earlier spoken about, and Markham looked at box splines very early on, etc. So then as Tony and Charles both pointed out, the people who were looking at surfaces at the time were also very much interested in geometric continuity. And that meant finite pieces to be put together. And again, there was this exchange between the two constant going on, which one would win, a finite number of polynomial pieces or infinitely many polynomial pieces glued together. And that is actually how Uli and I met up. We both were working on things related to geometric continuity, but then there is Uli's master's thesis that had a very, very good insight. It was picking up where Markham had left the theory in 1978. So this was many years later, what, 15 years later, 16 almost? What Markham had done is he had pioneered this idea that because things are repetitive in subdivision, you could actually look at an eigenanalysis, and so that was it could tell us what could work out and what wouldn't work out. But it was always, when you looked at it closely, it was always about meshes or nets that were somehow contracting, getting ever finer, but there were holes in between. And so Uli's insight was that you should actually start looking at surfaces if you wanted to do any differential geometry. Might be that someone in discrete differential geometry nowadays can do something, such an analysis, but we haven't seen that yet. So what I have in the background here is my first slide that I'll share with you in a moment if I'm share enabled. So the first slide is basically to my right, that would be to your left, or to the left of my head. What you see is this idea that subdivision surfaces really are a sequence of nested surface rings that just fit into one another ad infinitum. And then when you looked a little closer at this kind of paradigm, there's the picture to the right. I hope you can see it. And there what you have is you actually have what looks like n sectors, and you can treat each sector as if it was a piece of a spline. It's just a very strange spline in that it has a singularity in the corner. So that was the other insight, another way of looking at subdivision as just consisting of a, well, finite number of pieces, each of which had infinitely many ring sectors inside, and would then have a corner where everything is singular. And so that was the start of a book that Uli and I worked on for a long time. The reason it was so long is because the initial draft was very long, and we wanted to make quite sure that it becomes short in the end. And here I'll give Uli the microphone.
Yeah, hello everybody. It's so good to see so many well-known faces. Hello everybody. Yeah, Jörg, a small correction. My master thesis was on lead roots, which is very far away from subdivision. But then I started my PhD with Klaus Höllig, and he introduced me to subdivision surfaces, and he suggested to generalize Catmull-Clark to higher order smoothness, because this was requested by the automotive industry. From computer graphics, C1 is good enough, but the guys from Mercedes-Benz, which we collaborated in these days, of course, they wanted to have higher order smoothness. So I started to study the algorithms of Catmull-Clark and Du-Sabin, and also the known proofs at that time. I understood that the theory of Malcolm concerning the algebra of circulant matrices and so on, and the self-similarity, that these were very valuable ideas, but the so-called proof of ball and story did not satisfy me. By the way, does anybody know what happened to Ball and Story?
Yeah, Alan Ball was at the University of Birmingham. I think he has retired. Dave Story came to a sad end. He was found dead in the streets of Leicester.
Okay. Yes. Thanks. So these proofs were based on a study of a sequence of self-similar meshes, and this could not capture the differential geometry. So my first observation was that, as Jörg said already, that the analysis should be based on parametrized surfaces. And after rescaling, the sequence of surface rings is converging to a thing which is now called the characteristic map. And the characteristic map is carrying essential information. So the regularity and the injectivity of this map is almost necessary and sufficient condition for the C1 convergence of a subdivision algorithm. This was part of my PhD thesis. And shortly before I defended this thesis, I was invited to Oberwolfach and to give a talk there. And I went there, I met a couple of you there. It was in 1993. And I talked about singular parameterization and things like that. But a couple of days before, I had found this relation which is requested for C2 continuity. And it tells us that there is no variant of Catmull-Clark which is C2. And at the end of my talk, during the discussion, I mentioned this degree estimate, which is bad news, of course, in the discussions. And well, this caused quite a reaction. But then the dinner bell saved me, and I went to dinner. I was quite relieved that everything had went well. But after dinner, Mira and Carl and Tim Goodman came to me and they asked me to verify my claims. So I was in trouble because I had not written up a single line of the proof. And so we met after lunch, and for me it felt like an invitation to the Holy Inquisition. And we had a very intense debate. Mira, I don't know if you remember that.
No, I don't remember.
You don't remember? So I remember a phase of our discussion where you said the word "why" about 20 times in 3 minutes. So I was really confused, and I had a hard time to convince you. But after a second session in the evening, I had convinced you that my theory was at least plausible. So you invited me to Tel Aviv, and this is why I visited you in 1994. You and David, we worked on the construction of a C2 algorithm. And as far as I remember, we had something which worked, at least in theory, but the construction was so incredibly complicated that we never published it. Okay.
I found the write-up.
Yeah, so the write-up should still be there. Yeah, and 1 year later, I visited Jörg in Purdue, and this is where we actually carried out the proofs for Catmull-Clark and Dusebin. Yeah, so in my thesis, I only had the theoretical foundation, and the actual proofs were then accomplished in Purdue. And we also invented simplest subdivision as an example, not only for a very simple scheme, but also for a scheme which has a very unusual eigenstructure. For a 3-valent vertex, the subdominant eigenvalue is 8-fold, and still there is a C1 limit, at least in a theoretical sense. But I don't want to go into the details of this construction. Yeah, all these findings were summarized in our book, which when was it published, Jörg?
It was 2008.
Yeah, in 2008. And I found out today that there is an audio version available. I don't know if this is true. I found it on Amazon. I wonder how it works. So, Jörg, do you want to continue?
Yeah, I can say a word or two. I wanted to make the point how the theory comes back to actually create new subdivision schemes. The subdivision schemes will only win if they are sufficiently simple to implement. So that really hasn't happened. But Tony was mentioning earlier about the difficulty that piecewise polynomials present. Why would you implement both the refinement process of subdivision and the piecewise polynomials? And a good idea that stems from all of that is to use polynomials to predict shape, and then the subdivision surfaces to actually make it possible to get that shape in a very smooth fashion. So something called guided subdivision actually allows you to follow the outlines of a polynomial or piecewise polynomial and still get all the properties of subdivision algorithm. Difference that subdivision algorithms don't have sparse matrices, but they have relatively dense matrices. But on the other hand, they are very familiar to people who work with B-splines and do interpolation of boundaries with them. So these guided subdivision schemes, the first memory I have of someone using them were freeform splines by Hartmut Crouch. But I think that certainly Adi Levin, so it's not David, but Adi Levin published in SIGGRAPH a nice paper that where also the surface is essentially guided or helped by having a fixed polynomial. Why is there a problem with the subdivision algorithms? Well, you see the picture still behind me. Subdivision is rings and rings. If you do anything wrong in one ring, it gets repeated ad infinitum. And you can see that at three stages. At the very fine level, when you look at these subdivision algorithms, you will see that especially those that are somehow optimized algorithms, they'll have oscillations in them. That's because each one of the rings repeats a certain pattern as we move towards the interior. And we all know that Catmull-Clark is in fact a beautiful algorithm to teach analysis with, because it has in the limit divergent curvatures. It's not curvature continuous, as Uli just pointed out, but in fact, the curvatures go to infinity and they go to plus and minus infinity. This oscillation is then inherent in many of the classical algorithms. And you also see that you have difficulties with when you shine highlight lines on it. So this is going back to who's going to use it. If you want to convince people in the car industry, you have to have highlight lines that look just right. And they're very pernickety. They also look at points, point neighborhood, and so forth, which is maybe not so important for an animated character if there's something not as smooth as elsewhere. And so again, the theory of all of that goes backwards and, for example, creates things like guided subdivision, where basically you pick up the shape in the limit. It's almost like interpolating subdivision in the limit. And with that, you can create CK subdivision surfaces of reasonable shape. Finally, and just a quick advertisement, there's still even now, Ed is here, there's still now something to be said about Catmull-Clark subdivision rules. So what Markham very well expressed a long time ago is that the first step of your subdivision actually can have an oversized impact on the final shape. And the rule for n-sided facets in the Catmull-Clark algorithm is actually not a very good one. What it produces is typically flat spots, which the car industry, again, will not like very much. And so there is, in this conference, the SMI conference, there's one paper that deals with the extraordinary facet rule of Catmull-Clark and tweaks it a little bit to get much better results.
Actually, no, I addressed that that the real problem is if your triangles or quads are not regular, you're going to get bad surfaces. That killed our project 20 years ago. Maybe there's progress now. Maybe I looked at non-stationary schemes. Or actually a non-stationary scheme is the crease schemes that they use at Pixar, right? That's how they got around these problems. You know, these high-end guns in practice is not really a problem, really, at least from my experience. I'm just a practical guy, you know, and yeah, I used eigenvalues and B-splines or whatever.
Yeah, so I think the two are very much related.
Well, how come there's no general proof that a subdivision scheme with positive weights that add up to 1 always lead to a C1 scheme? Once you prove that, so many of my papers were, and I'm not bitter about it because I worked on other stuff. There's always the criticism, you didn't prove it with C1. All you need is a proof, a general proof, because of course there's C1, you can compute a normal.
No, it's.
You know what I mean? I'm just very practical and I don't really care at this point. I'm not involved in academic discourse. No, they're just, you can compute a normal. So what's the problem?
This is simply not.
I understand. C2 is not a problem. And you get these flat spots and everything. But why reject papers or research because you can't prove it's C1? I'm just throwing this out.
Yeah.
Ulrich, sorry.
May I comment on that?
No, but I'm sure you're used to this.
Yeah, so there's definitely a counterexample. If you tune the weights of Dusabin, you end up with a convex scheme which is not C1.
Okay, interesting.
There's a certain limit, and beyond that limit, which of course is makes no sense from an intuitive point of view, but formally it's as you want it. It's all convex combinations, and the limit has local self-intersections, which you certainly don't want.
Right. So by tweaking the coefficient, what's interesting with Dusabin, I did the analysis, never published it, is that you get a Jordan blocks.
You can have Jordan blocks,
very simple matrix. It's all Jordan blocks.
Yeah.
It's very interesting. So I never published this, but it's I was trying to do the exact evaluation for Dusabin, but I gave up because you have to compute Jordan blocks and everything. So it's, I don't know if people know about this.
So Yo, since I'm still unmuted, let me just, I think there's a very strong correlation actually between these irregular or extraordinary points or facets and the problem that you were experiencing. What you probably want is you want to have the outlines of your shapes so that the boundaries, the parameter lines align with lines of curvature. I think Dennis might tell us more about that.
No, I'm saying it's perfect. The higher continuity, the best, right? No.
Actually, can I also invite Ahmed Nasri to the, because he, from the very early times, he talked about the computer, how to use the subdivision in computer-aided geometric design. He may just add another point of view. Ahmed, do you agree?
Just unmute myself. Yeah. Thank you very much for inviting me, Jürgen, and nice to meet you all. But after such a long time, I haven't been in conferences for a while. My first involvement really in subdivision was due to Malcolm. When I went to University of East Anglia and I met Robin Forrest, I wanted to embark on a project. And at that time, it was like in June, and I wanted to go to Beirut at this time. And he said, when you come back, we will see. When I came back in September, he went to Utah, I think, to meet Rich for a sabbatical. And I left with just Malcolm to ask him about what could I do for my PhD topics. And initially, he suggested to work on an n-sided patches, like defining, he already had a formulation for a three-sided patch in terms of triangles and polynomials. And he said, why don't you go on and just explore that for n-sided or 5-sided and to begin with? And I consulted with Robin by email at that time, and he said, you know, I told him what other project I could work on, and he said, you know, there is this subdivision paper that you know, Du-Sabin and Ketmore and Clark scheme, and he told me that there are problems for this subdivision scheme if you like, you know, try to you know, implement an iteration on an open surface, it shrinks. You know, because by the nature of subdivision, it loses part of the boundary. And if I want to push this into CAGD, at that time, Bezier and B-spline, there was, you know, for open surfaces, they have control of these boundaries. But in the subdivision, if you do that, you will lose this. So here is a problem here that you have to fix it. You have to find a way to do something about that. And there are other issues in terms of CAGD, you know, for instance, interpolation constraint, surface-to-surface intersection, etc. The other problem is he gave me actually 3 ideas, and the problem was actually to look at the curvature of, you know, of Catmull and Clark. So when I consulted with my was Robin in Utah, he said, no, let's work on the n-sided patches. So I spent about 3 months. Of course, I didn't like it, but I like subdivision. I was, you know, I liked the idea. I worked on this for 3 months. By that time, by Christmas time, Robin came back and I had some little result. But I told him, look, I'm really, you know, after this subdivision, if you want to reconsider, let's discuss the issue again. And then he probably, I don't know if Malcolm was talked to him, and he was convinced that, okay, let's go for subdivision. So I started working with looking at these early in time and why these boundaries, how can we control them, but not introducing a new coefficients. And there is the one thing that I started with is really when you have a sort of n-sided boundary face, and what do you do with that in order to keep the subdivision? So I had to look at injecting some of these Chebyshev point and polynomial in order to change the geometry or adding some control point on the boundary so that when you do a subdivision, the user doesn't see this at all. It just see a surface that is completely in harmony with what you get in terms of B-spline and etc. And you know, if you remember, Malcolm, we had discussed this on a dinner at a restaurant in. I just want to bring Malcolm memories here. At a restaurant in downtown, where he said that this restaurant does not throw us away after we finish dinner. We can stay and talk even until 10, 11 p.m., which we did. So, you know, I really owe him so much for this progress and for pushing me into direction. And then we started, you know, to developing algorithm like interpolatory subdivision, initially for Du-Sabin, which one later on was moved to Catmull and Clark and other issues. And these constraints were exactly expanded a little bit, looking at various other constraints like curves, for instance, or normals. So you'd have a irregular data point with normals on them, and you want to interpolate them. Of course, initially, we implemented all these ideas in Du-Sabin because we want to start and see how things works, and in order also to pave the way for higher order subdivision to actually be involved. At that time, I want to mention something now because Tony also mentioned the creases and etc. I remember when I started early work on subdivision, there was one criticism about subdivision by a Japanese researcher, and he mentioned that this subdivision are not nice because they're all produce smooth surfaces. So I wanted to produce a picture in my thesis to show that this is not the case. But I didn't call it at that time creases, but it's just a curve in the surface, which actually has a C0
who was
continuity.
the person? Kuni?
I forget his name. It is in my thesis. I forget his name, but It's
With
there.
this Kuni, it
So
is interesting because you know that we dedicated this particular component.
no, not him.
Not
No,
Kuni?
not him.
Okay.
No.
Mhm.
But I produce a picture just to show that this is not the case, and you can produce a crease. But later on, I found out that okay, you can also explore the other constraint, like introducing curves also on the surface. So if you want a particular open curve on the surface, but at that time we only wanted the surface to be smooth across. And then, we also expanded this to controlling even the curvature across these curves. And that, led me to something called the polygonal complexes, which are minimum, let's say, a minimum network, minimum data point for each subdivision scheme that actually, when you subdivide, it converges to a curve rather than a surface. And the nice thing about these complexes is that they carry with them, as you subdivide them, they carry with them cross-derivative information. So you could control the tangent, you could control the curvature, because they're embedded. I mean, if you embed these strips into a particular network, the curve, you get two issues at the same time, two birds in one stone. You get the surface, and you get the curve, and you get the curvature, and you get the tangent plane, etc. So, and then eventually me and Malcolm wrote a couple of papers on, summarizing all these interpolation constraints. It was published in the Visual Computer into 2 sequence issues. This one also led to, after we did most of the work on the Du Sabin, we start moving into Catmuller and Clark, and did like skinning of Catmuller and Clark subdivision surfaces, where you have the issue of lofting that was initially defined by curves with uniform control point, and that was a constraint in CAGD. Now you can have curves with different control point, not necessarily the same, and you can produce a surface across them with minimum data point, as you can see. And then, we also explored the possibility about, with Gerald, about rational subdivision, and piecewise also produces piecewise circular arcs with Brian Wyville. And I came across by this, idea in their paper, which was not published. And of course, computing volumes enclosed by subdivision surfaces with York Peter and other researchers. I think also the what wasn't mentioned a lot here about the ternary or other subdivision scheme, like the one that we published also with students of York a few years ago. About ternary subdivision scheme for quadrilateral meshes. It was based on some of my master student output. I want to also mention that the idea of the complexes that have curves and cross-derivative information was actually used by defining subdivision surfaces by initial curves and with filling hole regions inside them. So if you have an unsided hole into this complex, you can fill it with meshes, and then you can inject it to a subdivision system. And by the way, we use this in close modeling, in a PhD thesis for filling and attributing to close modeling design. I feel that the issue of non-uniform recursive subdivision, even Catmuller and Clark, which was touched upon with the work of Tom Söderberg, and most recently in the T-spline and the T-NURCs, was not expanded further. Although we did more work on T-spline, much more on subdivision or T-NURCs, I think that area maybe still need to be explored.
Yeah, actually, that
I
was
hope.
I wanted to talk about that direction also.
Yeah,
Thank you.
yeah,
Yeah.
yeah.
Mhm. Okay, probably
I
like
think
the
Charles Loop addressed this problem, and
Mhm.
I sort of agree with him. That you want to keep things very simple, but not too simple, right? So
Yeah.
we did this experience in Maya where we went from the T-spline idea to hierarchies of subdivision surfaces.
Yes.
There was so
Yes.
much overhead that
Yeah.
we abandoned that. Maybe they resurfaced that. I'm not saying you shouldn't be doing it. I'm just talking
Yeah.
about my experience. And
Yes.
to me, I like things to be very simple.
Yeah.
Optimize them very easily. And this whole hierarchy and you're talking about the NURSS paper, right?
Yes. Yes. Yes.
Yeah,
Yes.
exactly. From
Yes.
98. Yeah.
Yeah. Yeah.
Yeah. It was in the same session where I had a paper. Yeah, I
Yeah.
remember it very well. It's very complicated.
Yes.
So if you
Yeah. Yeah.
no, but
Yes.
I'm not saying you shouldn't research it, but you have to prove us that it's. I mean, if you
Yeah.
want
There
it
is.
to be adopted in industry, right? You have to prove the benefits,
Yes. Yeah.
especially now with the hardware on GPUs and whatnot. Yeah.
Yeah.
No, I'm absolutely not saying you shouldn't pursue this research. Of course not. And in the nurse paper, that's how you
Yeah.
pronounce it. Yeah.
That's correct. That's
It's a
correct.
great
Yes.
paper. Yeah.
Yes. Thank you.
So probably we can go to the Joe Warren and his contributions.
Yeah, let me share my screen here. I will have a few slides. I'll go very quickly. Don't worry, I won't drag this out. So let me share my screen. So I first want to just thank Ergen for organizing this. It's great to get a chance to see all my friends and colleagues after a long break. I haven't actually worked in this area in almost a decade. And so I thought I would start off by just saying a little bit about what I've been up to here, because I haven't seen many of you in a long time. I've been a professor at Rice University since 1986. I got my PhD from Cornell, and I've worked on kind of geometric modeling and computer graphics for basically the first 25 years of my career. I worked with a faculty member named John Hopcroft, who was very well known, and he only did geometry for about 2 years. And so when I graduated and went to Rice, I really didn't have any hooks into the geometric design community. And so I want to thank Ron Goldman, because Ron was really instrumental in kind of introducing me to the community and getting me kind of experience in working on this. And then later, from about 1990 to 2010, I worked on various things in subdivision. And also I had a lot of contact with David and Nira, and they helped me a lot also. I had a great time visiting them in Tel Aviv. The title for this is Subdivision Methods for Geometric Design. I wrote that with Henrik Weimar, who's at Airbus, and I had a lot of help from Scott Schaefer, who is now the chair at Texas A&M. It was really a combination of things that I had learned from the others in this field and some of my own ideas that I kind of synthesized into my own unique view of subdivision. And I'll say kind of a few words about some of the things that I kind of viewed as being important here. Like many of you that work in academia, I got sidetracked in the late noughts and became department chair. And that kind of started my slide out of doing research. And then in 2013, I went off and became very involved with Coursera and built some specializations on there. I had a good time, but it ate up all my time on there. And now I'm basically kind of swamped with administrative work inside the department. I'm gonna have 2 slides, so don't despair here. I just want to say a little bit about the ideas from the book and where I worked on kind of basically the last 5 years of my career, because I want to provide kind of a different perspective from what I've heard here with the various talks. And so a lot of the talks here are focused on meshes and building meshes that are smooth or maybe C2. And there's a lot of great work on that, and that's very useful in industry. But I was inspired by some of the work from basically approximation theory. And the idea was they want to think about ways to build spline spaces and have nested spline spaces that could lead to nice geometric algorithms for processing those splines. And so just a little bit of notation, we have a bunch of knots, and the knot sets are basically getting refined. We're adding more knots. And the key thing to note here is we're not necessarily doubling the knots or quadrupling them. We're just putting them in anywhere we want. And so you think about this as more like knot insertion. And so when you think about explaining how splines work to folks, the goal is to basically build a set of basis functions. This is a vector over each of these knot sets. And what you want to do is if you have a set of coefficients on the coarse knot set, You have a function over this coarse knot set. And what you want to do is be able to subdivide it. You want to be able to express that same function in terms of the finer basis functions. And this is the critical point here, is you want those coefficients to converge to the function. So this is the setup. So let me give the payoff. This is one slide. I'm just going to talk about this for a few minutes. So the reason I got into doing subdivision was when I was a graduate student at Cornell, we had a class on geometric design, and we talked about cubic B-splines, and the people that taught it were not very well versed in approximation theory. And so we literally said, oh, it's a C-wise piece, it's a C2 piecewise cubic, supportable for intervals. And we spent all kinds of time building a representation of it in the monomial basis and trying to figure out how it worked. And it was god awful. And so for me, it was a revelation when I saw some of the previous work that had been done on subdivision for things like cubic B-splines, because there was such a simple geometric approach to working with a spline where you never had to worry about those underlying functions. You just worked with the coefficients or the control points, and you had simple discrete operators that did that. And so that inspired some of my thoughts about how to go forward and how to generalize subdivision to things like knot insertion. Like there's some beautiful algorithms for knot insertion. And I think about that and say, can we have something that will give us a way to understand how knot insertion works, that is kind of works with subdivision, works with knot insertion, and it works over a variety of domains, not just the line, but the plane, and maybe on a manifold like a sphere. And so here was the takeaway of the kind of the approach that I talked about in the book. And it's something that I pushed in kind of the last 5 years that I actively research. And this is inspired by work by David and Nira. They did some very nice work on basically preconditioners for Green's functions to meet bell-shaped basis functions. And so this for me was the thing that kind of came to my mind was the most important idea, is that you can think about building subdivision via a differential operator. And this could be just like in the univariate case, a derivative or a second derivative or a third derivative or a fourth derivative. And in the bivariate case, it'd be maybe the harmonic operator, the biharmonic operator, or maybe some directional derivatives if you're thinking box splines. And so the goal is you just discretize that delta over the knot set. And that's the whole game. Just you have to figure out how to discretize correctly. And then there's simply a commutative relation that governs how to refine your points. So here's the refinement relation. You've got some points on the coarse knot set. You refine to get them on a finer knot set. Matrix S that does that. Hopefully it's nice. And so the matrix S has to essentially operate with this difference scheme. And the way to understand this is if you substitute these in, you get this difference relation. It simply says if you have a set of coefficients, control points, or whatever, and you difference them, you get some differences. And if you want to map that onto a finer knot set, you upsample, you put 0 at the new knots. And then you need a set of control points that when you difference them, you get the same differences back. So Malcolm said something interesting, said, but finite differences aren't really are too complicated. But the point that I kind of tried to pursue in the last part of my research was that there is a way to think about some of the algorithms we're doing as being finite difference schemes. And the key is to choose those differences very carefully so we get the things that we're used to. And then if we can build new ways to do differencing, we can get new algorithms out of it. So for example, B-splines, if you use divided differences, you get kind of the standard uniform subdivision schemes, but you also get non-uniform subdivision schemes, things like knot insertion. The local rules pop out exactly. Box splines that are uniform, they can be thought of in this way very easily also. Kind of the last paper that I wrote was talking about ways to do this over manifolds and using the harmonic operator and the biharmonic operator. And the critical thing here was that we had to discretize this operator. And so for example, the plane, the discrete Laplacian is a wonderful way to discretize this operator. And if you do this, both in the plane and on manifolds, you get really nice, well-behaved basis functions. They're not local, but they're localized, they're a bump. And you have algorithms for subdividing these basis functions that really boil down to solving a finite difference scheme. Now, because these are localized, you don't get local rules, but you get rules that are easy to solve with some kind of finite difference solver. You can basically solve this because these are all sparse matrices. You could solve it very quickly. Because this is beyond subdivision, I have something to suggest to those young folks that are here watching. if you want to think about where to go. So I worked on the biharmonic case extensively. And so it basically, the last paper that I wrote was something that talked about doing the biharmonic case on manifolds, things like spheres and tori. And I came up with a pretty good approach, but here is my challenge to folks for kind of where to move in one particular way. And that is to think about what are the correct analogs of divided differences in the plane or on a manifold. Just doing things like, for example, iterating the discrete Laplacian works okay, but my sense is there's something better here. That you need to think about ways, for example, what's the analog of a higher order Voronoi diagram? From that higher order Voronoi diagram, can you go through and build higher order analogs of the divided differences? And so for me, this is kind of where I spent the last few years working. And so the thing that I would say, I'm more of a mathematician than probably many of you are, is I have a mathematical bent, and that is this relation here is the critical relation. That if you want to think about these schemes as being different schemes, that what you really want to do is when you're refining your mesh, you want to replicate existing differences, and then at new knots, make the differences be zero. So I promise I'd be quick. That's my little blurb on this. I do have an extra story that I can tell about Schroeder, but I'm going to wait until the end. And if we have time, I'll tell you a story about Peter Schroeder, because this was my fondest memory of going to the various conferences to meet with all of you.
Okay, now it is time to go to some fancy algorithms. We can start with the Leif-Kobat with the square tree algorithm, then Lewis-Valho 4-8, etc. We can go like this. Leif,
I think Peter has to leave at some Peter has to leave at some point. So
okay, if Peter, do you have to? Okay, maybe you can.
I think you have a hard deadline.
Well, I'd love to jump off of what Joe just said. His book was
that's a good idea. Yeah,
that was a great inspiration, and it's still my standard when I teach subdivision, which I don't do very often these days. But when I do it, I very strongly follow his ideas from the book. So what I want to throw into the mix here, into the hopper, is the whole connection with wavelets, because that's where I came from originally, from the wavelet world. And I was looking for more general ways of constructing them, and chanced upon subdivision. And in fact, the Michael Lounsbury's thesis, who worked with Tony DeRose at the time, where they had constructed some wavelet-like constructions based on subdivision and subdivision surfaces. And in fact, this was the beginning for Wim Sveldens, who tried to figure out just what are they doing? What is this? To develop the lifting scheme, which then became a big deal in wavelets as a very general construction. So for me, that was really the entry point, and where a lot of interesting things started happening, and what motivated me to think about simple operators that get cascaded. And that's what led to the averaging, primal dual averaging, which, by the way, Jos, if I remember correctly, also had simultaneously worked on independently of us. And then later led to other constructions with Peter Oswald, for example. And this whole idea of having small little operators that are cascaded together became a thread that came originally from this wavelet world. So for me, that's a very important acknowledgement, and also speaks a little bit to what Joe was just saying, these potential directions of going to manifolds, using more complex operators like Laplace or B-Laplace in those settings. There's this whole connection with discrete differential geometry. There, Pixar also still is leading in the research. Fernando de Goes really has some work on subdivision circulars, for example. So these things keep percolating, keep bubbling outward, which is one of my great pleasures in this whole business, even as I don't really do subdivision anymore these days, more discrete differential geometry. So I just wanted to throw that into the mix here. Thank you.
Thanks. So, Leif, do you want to be the next?
I've lost him.
Tony, do you have
the
whole wavelet connection?
Is that
on the
working
wavelet
now? Sorry.
Works.
Yeah. I'm just going to jump in here on the wavelet connection real quick. So I was starting to get interested in subdivision more and more. And then Joe came to visit. I spent a sabbatical year, and Michael Lounsbury was looking for a thesis topic. And when we finally made the connection between subdivision surfaces and wavelets on manifolds, that was the moment when I said, okay, this is the way we've got to go. That was really the tipping point for me. Yeah.
Okay, I think Leif, you can take over.
Okay, if I can share my notes here. So this is the situation that I found when I actually started working on subdivision. The analysis was fairly understood, and from the practical point of view, there were some schemes for triangle meshes and some for quad meshes. We had primal and dual schemes, and among the primal ones, there were a few interpolatory ones, and like all the names that you see here are actually in this video conference and have talked already. So when I started doing research in subdivision, I just explored different variants. So what else can you do? And one obvious gap here was that there was no interpolatory quad scheme. So this is something that was kind of my first try to develop a new subdivision scheme and use the analysis methods that were available. And then I struggled for a while in figuring out what could be a dual subdivision scheme for triangle meshes. And this is not so obvious because, as you all know, the quads are self-dual, so it makes sense to map quad meshes to refined quad meshes in a dual sense. But for triangles, this does not make a lot of sense because the dual is a hexagonal mesh. So I played around with it quite a bit, and eventually I figured out that if you look at the dual perspective, instead of trying to subdivide triangles in a dual fashion, go to hexagonal meshes and just try different ways how you can refine those. And then you find this splitting scheme where every hexagon is replaced by a smaller hexagon, but rotated by 30 degrees, and then connected in the way that you see here. And I was very happy that I found this new twist how to refine hex meshes. And if you go back from this dual setting to the primal setting, exactly.
Actually, this explanation is so exciting. I'm pretty sure with the Peter and Zorin, Dennis, because for me, because we talk about another idea and then it was very similar. Sorry, I didn't know that you came up exactly this way. This is very exciting. Okay, see you.
Yeah, okay, this is why it's called research, right? We research the same things.
Nice, very nice, yeah.
Okay, so and that was pretty much the birth of this subdivision scheme, and finding the rules for the new points that had to be inserted for the triangles is obvious. We take the midpoints of the triangles, and then what remained to be done was figuring out the rule how to update the old positions. And out came a subdivision scheme that had all the properties that we knew from the other schemes, C1 continuous is easy, C2 was impossible to achieve. So we ended up with something that is almost C2 continuous, and practically it can be used as all the other subdivision schemes that I had in my list before. Another aspect that I would like to mention here in this historical overview is, besides filling that matrix here, so that for all the special cases we now have subdivision, we now had subdivision schemes. Actually, this appeared in 2000, and I think that was my last paper that I wrote on subdivision, even if I'm still getting papers to review these days. But this I stopped working in the field quite a while ago. But this other aspect that I would like to mention is that another thing that I explored was the so-called variational subdivision. So instead of refining polygons or meshes by figuring out fancy rules, how local averages on control points can lead to new control point positions, I was just changing the paradigm by saying, like, this is now what happens for a polygon. If we want to refine a polygon, we can make it interpolatory so that every other control point in the refined polygon coincides with the old ones. And we have to figure out how to place the new ones. And in the case of variational subdivision, I propose to do this by an optimization scheme. So we define a target objective, say the case differences on the refined polygons or their magnitudes should be minimized. And in that work back then, I could actually show that, at least for curves, if you minimize this, then this is of course equivalent to solving a linear system that sets half of the second or two case differences to 0. And you can prove that this actually produces CK-1 continuous curve. So that's very similar to what you see in the continuous case, where like minimizing the case derivatives of a function leads to the well-known spline functions. So that works for curves quite nicely. For surfaces, the natural generalization of doing this is to replace the difference by the Laplace operator and then refine meshes in a way that after the refinement, the sum of all the Laplacians or bi-Laplacians or higher order Laplacians are minimized. And in fact, that also creates nice and smooth meshes that quickly converge to an overall fair shape. However, that relation, of course, I was unable to show. And I think there's no evidence that no matter how high you put the exponent here of the Laplace operator, you can still only expect to have C1 surfaces. But this is actually when I quit this field, because doing further analysis of this in the surface case was maybe too complicated for me. All right, thank you very much. Very nice, thank you. So we still have Dennis and Luis. Is Luis maybe ready to be speaking?
Yeah, sure.
Great.
Okay, so let me start by saying that I'm really glad that Peter and Leif, just spoke, before me, because my work in this area has a lot to do with them. I know Peter for a long time, and we both been involved in our PhD thesis with wavelets. So one of my motivations to do this work on subdivision is related to wavelets. And I remember meeting Leif at the Eurographics 1999, and he was explaining to me his square root of 3 subdivision. And at that time, I had already pretty much developed the 4/8 subdivision. And we started discussing, schemes for triangular meshes, quad meshes, and everything. So, and also, I mean, there was a very good connection with Dennis Zorin and Mathieu de Brun, because we both, used to meet in conference like curves and surfaces and C-graph and talk about all these things. So I think there's a very nice connection with all those things. And, my path is kind of divided in two parts, because, one way I went through a very practical geometric modeling thing, like with, mesh simplification and multi-resolution, which has to do with the practical way to do wavelets. But on the other hand, I was investigating the mathematical underpinnings of those things, like, simplification methods and combinatorial topology. And I think the good thing about the 4/8 scheme is, one hand, well, there are new ingredients that hadn't been exploited in the subdivision community up to that time. Like, one is adaptivity, because the 4/8 scheme sort of combines in a very nice way like triangle meshes and quad meshes, because it has a simplicious structure, but with underlying quadrilateral structure. And so this is very nice for adaptivity. And in a way, the square root of 3 can do some things like that, but I think the 4/8 structure is much richer because you have 2 kinds of parameterizations, both at the same time. And this has to do with also, like in a more like a profound philosophical way, with the relation between primal and dual schemes. And this leads naturally to the factorization of the subdivision schemes, which is something that at the time Dennis and Peter were working also. So the things of, as Peter and Lars said, that this is research, right? So the ideas flow, and people are like kind of synchronized, with this waves like around the globe, right? But the other things I think is very nice about the 4/8 scheme is that it allows us generalization. It's like a frame that you can actually devise like subdivision grammars, and this gives a way to understand many other subdivision schemes. So this is the work I published at SGP with the subdivision grammars, so that you can kind of include the factorization, this combinatorial topology structures, and naturally leads to all these other things, right? So, and I guess with that, I think I'm going to pass to Dennis, because Dennis helped me a lot in the continuation of this work, doing all the analysis, and was a good partnership. Is Dennis here?
Yeah, Dennis here.
Yeah, I'm here.
Okay.
Dennis
Thanks,
and
Luis.
Peter, you can also talk about the dual and primal subdivisions, like
Yeah, sure, yeah.
Yeah. Mm-hmm.
Well,
Now
I
that
actually want
it
to
is
talk.
all related, like, yeah.
Yeah. I actually want to talk about something else, but it seems like we have quite a bit of time, so I'll maybe say a few words to complement what Luis was saying. But just to get started, Peter has mentioned that his path to subdivision started with wavelets. Actually, so did mine, but it's kind of in an interesting way. I took a course when I was a first-year grad student on wavelets, and at the same time I was trying to figure out what is it I'm going to do for my PhD. And somehow I got this idea that I want to do something with surfaces. There was not clear understanding. How do you think about surfaces in terms of bases and things like that? And I said, well, maybe it sounds like a good idea. And around the time, was when Peter joined Caltech as a professor. So I actually started as a PhD student before Peter was there. And I thought he's just a rendering guy, so there's no real overlap, but that's exactly when Peter also decided to look into geometry. It's very lucky coincidence, because I had no idea about anything. So he introduced me to subdivision from wavelet perspective. I ended up not doing much with wavelets, but that's how it all started. But to maybe get back to the kind of the theme of primal dual schemes and 4/8 subdivision. When I was working on my thesis, I worked quite a bit on theory of subdivision. Actually, it turned out to parallel with Uli Reif on CK. I, of course, knew about his work on C1, didn't know about that he was also working on CK. And one of the things that I really was trying to figure out, how is it you automate this analysis, right? So C1, not CK, but how can you, like, just someone gives me a rule, how can you just tell, is it C1 or not, without doing some special work and a lot of calculations? So I figured something out, won't go into details how to do that, and well, almost, not entirely, but almost a semi-automatic way. And so there were all these different schemes that people were coming up with. So this was a good testing ground for that idea. That's one of the reasons why I got interested. But another reason was that it seemed this was something really magic about Catmull-Clark, and I'm going to get back to this in a minute when I talk about the actual topic I want to talk about. These rules, you can tweak them in many different ways to make them theoretically better somehow, in one sense or another. But it always somehow ends up making the surface look worse. And so there's something very natural about this generalization that was in that paper that actually make it look good. So these rules kind of the right thing. The small deviations you can do, but anything more dramatic that really messes up the overall shape of the surface. So I want to see if something which is, say, high order, more general in similar spirit could be done, and that's kind of the primal dual ideas. 4.8 is also kind of a little bit in that spirit. In addition to, from my point of view, being a very interesting case in terms of how can you analyze such things. So one more thing I would talk about, maybe deviating a little bit from other things that people have mentioned, is a scheme which is not really a subdivision scheme, it's a surface construction scheme that we came up with in early 2000s, but it entirely based on the subdivision work. And I thought that's interesting to mention is because it kind of shows that there's certain ideas that came from all this work on subdivision, both theoretical and practical in the 90s that actually go beyond that. And it doesn't really matter how we call it subdivision or not. So let me share my screen and show you an example. I also all right, so yeah, also Ergun had this great picture of Buzz Lightyear, so I thought in infinity surfaces would be a suitable topic for this section. There are these basic questions about subdivision that a few people worked in. How do we make this C2? How we go beyond that CK or C infinity? Of course, there's Jos's great solution to evaluating them at arbitrary points. And all these questions, they are, of course, very important for the context that we all know and like, geometric modeling context, but they're also essential in scientific computing. And in early 2000s, this is when I started working on scientific computing side of things, not just simulation for graphics, or not as much simulation for graphics, but solving PDEs. But of course, it involved complex geometry, right? Not surprisingly, perhaps. I always was a very big fan of geometric problems. So after many years of work, that's what we ended up with. So this is a very large scale simulation of flows of deformable particles flowing through complex geometry. Actually, that particular mesh that's shown here got from live cobalt. It was extracted from, I think, a CT scan of blood vessel system. And so what we do is simulate all these cells flowing through that. And sure enough, this is not quite a subdivision surface, but this is something that's actually pretty close to that. And these questions that I mentioned are exactly the ones that we had to deal with when we started working on representations for that. One thing I should mention, this simulation that you're seeing, this is based on, it's called integral formulation of PDEs, which basically reduces solving all problems to problems on solid surfaces. But what we need to do is to compute integrals. Compute not just any integrals, you have to compute singular integrals. And to make it really large scale, you have to make it very high order. And to make a simulation high order, you need a very smooth surface. It's related. You cannot go beyond the order of smoothness that you have in the surface. So I had a brilliant student back then, Xing Ying, who went on working on many interesting things in numerical computing, but he started working on subdivisions. Actually, his first project was on non-manifold subdivision. So sure enough, we thought about subdivision as the first option, but as Leif said, it's just too difficult to make anything smooth enough. So we started to kind of think about other options, but we had all these ideas that came out of subdivision. Let's say the characteristic maps are really can be thought of as C2 atlas manifold charts on the surface. And then actually a lot of the stuff that I did on subdivision actually was based on my conversations with Tom Duchamp. I don't think he was mentioned here, but I think he worked a lot with Tony's group back then. And he was actually, I didn't talk to him that much, but every time I talked to him, actually, it's actually influenced what I'm doing on the math side quite a bit. So in particular, he introduced me to this idea, actually coming from some old geometry books about how to build C infinity atlas on surface, and that's what we started with. But conceptually, it's actually really similar to what happens with subdivision surfaces when we try to analyze them locally near extraordinary vertices. So you have all these local charts and just to build on that. So actually, from that point on, it was actually surprisingly easy to build something that is as smooth as you want, has an explicit parameterization. You can actually write down the formula. It will be a long formula, but you can write down one for the surface. But here's the catch. So we knew how to build this thing. We had no idea how to actually determine the coefficients of these basis functions that we built in a way that it looks reasonable and it's efficient and it's really everything is a linear relation. So to make it all easier computationally. And this is where, aside from the general ideas, but this is where really Catmull-Clark comes back in, and in the spirit of what I just said. You know, if you just look at it as a method of refining meshes to get a nice surface, in some ways nice, probably can be somehow formalized fairness or some other concept, it's really hard to beat unless you go to variational subdivision like Leif did, and there were very many other approaches. So you have to really work hard and solve variational problems to improve in it by much. It's actually pretty good. So Catmull-Clark surface here serves as a guide. So we do have all these nice properties that we need on the numerical analysis side. So you can see like a picture here. We have really nice parameterization near extraordinary vertices. We have our smoothness. Everyone behaves as expected. But we also get the good looks of Catmull-Clark in this setting. So that's sort of going back to this to this picture. This is actually, there are many things under the hood here, but this is really was one of the main things that we came up with that make lots of other things much easier to do. Okay, so that's the story I want to tell, because subdivision is a pretty exciting area. I haven't done much work on this, but actually I keep doing some work on this on and off. It's late, I think it's 2017, we did a little bit of work on this. And I think what came out of it is lots of great ideas that we can continue building on.
Thank you very much, Dennis.
Sorry, Jörg, did you say something? Mm-hmm.
No, I wanted to say that you're going to wrap up the session, I believe.
Okay, so I will talk about my experience. My experience is a little bit different because I came from implicit surfaces and fractal geometry. Like originally I worked with the Michael Barnsley. Then in the 1990s, I wanted to turn the implicit surfaces into something very much like parametric surfaces. We should be able to control them, that kind of stuff. Like I did like many work. We had the implicit surfaces conference. If you listen to this beginning part of this, like in the SMI conference, eventually, actually, this what we show, like with the introduction of the subdivision surfaces, and then with the success of the subdivision surfaces, it was clear that implicit surfaces will not be able to win. Actually, Charles' idea was like implicit surfaces was even much more complicated than, because I really liked that paper from Charles, but it was even much more complicated. I was working on it, and then my obsession was changing the topology, but I was able to do with the implicit surfaces in the real time. I was able to control the shape spots, etc. But it was still not it was very infancy in that time. So around that time, I started to work the GNRChan. We formalized the how we can handle the polygonal structure. Then it ended up like then it became excited because I was able to show that we can change the topology of with the implicit. Let me share my screen. And it's because it can be, it was our 2000, like these are the some pieces we did, I did it before. And then this is, I believe it's 2001 paper. So what I will do right now, just to delete the edges. When I delete the edges, and then in the, like I can just separate like the, oh, actually I didn't delete the edges. So okay, let me just introduce them. No, this is the edge collapse. This is the delete edges. Let me just do it before beginning, like the, and then. And I was doing edge collapse, like edge collapse is like a splice operator. This is the delete edge operator. So let me delete the edges, you will see what happened. So we got this, and then I can separate into two. Or this was the exciting one. And then this is a little bit bug. Like I was able to introduce I will just introduce the insert edge between two faces. And then I was able to get the whole. That was exactly what I want to do with the implicit surfaces. And then I was able to do it with the polygonal meshes. So in the 2001 or something like that, I think I went to SMI conference, like to present one of these ideas. And then Malcolm gave a speech, and then he said that I was not really thinking about working on the subdivision surfaces. He said that there is an open question here. And then, let me just simplify this, because we already have a structure. And then, and then in the hotel room, I drove something. That was exactly what, like the life show us, like the, and then we implemented, and then that was a paper, like I will explain all this stuff. Like I call it the honeycomb, and then it can create a, this is actually a dual of the square root 3 algorithm. But in the same time, several groups, like including the Peter and Dennis group, publish in this one, including myself, in the different places. So I thought that I should create something which nobody could create it. So I came up this 5 conversion. This is a pentagonization algorithm. And then this, like basically it creates the pentagon. If you apply the dual twice, and then you will get the nice pentagon meshes with this one. And then this ended up like pentagonal stuff. Then as a result, like after the Malcolm's idea, I ended up to putting all possible cases here. So here, 3D conversion, like, so give me any polygonal mesh, and then if you apply the root 3 or one of these algorithms, they turn it to triangles. This turn it to the 3 valence vertices. And this guy's like Catmull-Clark, or Catmull-Clark turn it to everything to the quad, or stellate with edge removal, create everything, like simplest turn it to everything, 4 valence vertex. There's an equivalent of this. And then loop is, in this case, why I call it the preservation, because the loop subdivision doesn't turn any polygonal mesh into a triangular mesh. Like I can start from anything like this. And if I apply the remeshing rules of the loop subdivision, basically it works like this, and then this pieces continue to be quad. So then after that, I wanted to come up something really, really strange, because I was working on the fractal geometry, and then I will show you this guy. It is not under the so it is called the Sierpinski operation, but it is not really Sierpinski. I will show you. if I apply this, you see that I ended up pyramids. It looks like a self-similar, but if I apply the next one, the top is the like a normal pyramid, but these guys are tetrahedron. They look like tetrahedron, but they are not. Actually, this whole thing is a connected manifold surface. Let me just apply the, therefore that's the, like I will apply the Dusabin and then you can see the, how they are manifold surface. So as a result, if you consider this guy as a subdivision, there is too much to do with the surfaces also. Like the, because the, this is definitely not a fractal surface, because the, actually that was the one problem. I can stop share and then I can say that. That was the, what I had the problem with the Barnesi's work, because it was creating a bunch of disconnected pieces. But what is excited about the, like the subdivision surfaces, we ended up as still at two manifold, like in each stage, like just to even continuative, like we don't even have to think about the C1, C0, like even the C0 continuity wasn't there, like in the sum of the fractal algorithm. Actually, that was my point on this one. This was an SPM paper. And then, so that I don't want to go further because it is almost 1 o'clock and everybody is tired. So if you want, you can stay, I can create the, like the, this breakout rooms, you can go to the one room to another, or if you want, like if nobody wants to continue, we can stop. I will just stop recording now. Is that anybody wants to continue? You must all be tired. Like,
well, I want to say one thing. This journey through time and space has been incredible. I've loved it. It's amazing to see how it's developed, all the ideas that have come in, interfacing with the real world to push it. It's really, it's been a wonderful journey. I love what you put together.
Okay.
Yeah.
Yeah.
I'd like to just respond. Malcolm left me completely confounded with that remark that Robin and I both solved this one in one night. The only sense I can make of that is that there was strong speculation that Chaikin led to piecewise quadratic. I don't think Robin ever wrote anything that showed it, but maybe we got together over a beer and said, yeah, it's got to be that. And maybe that accounts for it.
Yes, you're right.
Yeah.
Who said that?
Me. He did not write anything, I think.
Robin reported back to me saying that the following day, Rich and he had got together and had independently come to the idea that, yes, this was definitely a quadratic B-spline. Now, this is second hand because it's what Robin told me.
But no write-up.
I'm sure the idea was agreed upon, but we had, I don't remember anything, that was mathematical that showed the result.
Oh, maybe not. The first step is identifying whether or not it is true or not, and proving it is you don't even attempt it until you know it's true.
Okay, so that resolves it in my mind, Malcolm.
Yeah.
I need to step out, but I've really enjoyed this.
Thank you.
So thank you so much.
That was excellent.
Yeah.
Can I just throw in two ideas which have come? I've been listening to everything, even though I can't see you, and you probably can't see me. One is that I think
Malcolm, we can see you. We can see you.
Oh, great.
Yes.
We can see you and hear you.
Right. Well, what I say is more important than what I look like. Okay, I don't think Hölder continuity is that important. It's people have focused on it because it's something we can analyze. I think that what is really important is the artifacts, the slight ridges and bumps, the changes in curvature. And we managed to handle this by making sure that our knot flow follows the flow of the shape that we want. And what's the shape that we want? Well, we don't actually quite want the knots to follow the principal curvatures. We probably want it to follow the ridges, which are the lines of maximum of transverse principal curvature.
Yeah.
That Boris Clemenson, who was working at Dassault at the time, but did a PhD in Cambridge, asked me to translate his thesis. And this became very obvious that along the leading edge of a wing of an aircraft, then if the wing twists, the principal curvature lines don't stay at the leading edge, but the ridges do. And that maybe we've got something there to help us guide where we put the knots. Right, let's see if I've got anything else to say. Oh yes, sorry. In panel 2, the mainstream, we had a great success story of subdivision in graphics. But in computer-aided engineering, we've got design and manufacture. And when you're designing for something that really works, you've got a whole lot of other constraints rather than does it look good. Graphics is the easy one, because if it looks okay, it is okay. If you can't see the problem, there isn't one. And you can't see anything fine on the pixel. But in real engineering, we've got problems of, well, the shape of this car has got to handle the fact that there's an engine underneath the bonnet, underneath the hood. It's got to have reasonable aerodynamics, otherwise it won't go very well. And so the link between the design and the analysis of what our real shapes are go way beyond, in terms of problems, the mere problem of making an image which looks a bit like something that you can recognize. So I was a bit sorry that the mainstream does actually only really refer to graphics. But I think we've got a whole lot of bigger problems, more interesting problems, problems with even bigger payoff in looking at the way that subdivision might be useful. Now, this comes back to the big problem with Catmull-Clark, which is nothing to do with not C2 at the extraordinary points. It's to do with what happens at the edges of a face, where the curvature along the parameter lines goes to 0.
Actually, Malcolm, I can, because you remember, I show that those problems in my cases, because I can create extremely complex cases with my software, and then I can show that problem. Unfortunately, generally the people use the simple cases, and then you don't see this. It has to be crazy. It has to be crazy, and then I can create those crazy shapes. Yeah, like the crazy faces, actually.
Well, I'm mentoring a guy who is trying to make subdivision usable in design and analysis. And one of his big problems is to get things working nicely in a BREP. Now, the graphics models we've seen don't actually have edges in the BREP sense. They have things that you'd like to be sharp edges and things you'd like to be semi-sharp, somehow scattered. But the BREP is something which nails you down very hard. Look, I think I've been negative enough. I'm going to stop. And I would like to apologize for not being able to see everything that everybody's done. My Zoom has just, well, I mean, quite early on, it collapsed and wouldn't do things. So
actually, can I add one more things about your negativity? Like, it's not a negativity, but another big problem. So we are always talking about the very high valence vertices. Actually, low valence vertices is also a problem. 1 valence and 2 valence. Like those create the problems in both subdivision cases. So like we assume they don't exist actually, but as soon as you introduce them, but you can use as a feature. That's another way of thinking about it.
Yeah, my view is that in the engineering context, 3s and 5s with Catmull-Clark are enough. You don't need high valency. And I did actually put together a paper at one of the Norwegian conferences, which said that if you have a 2-valent vertex, you can actually get C2 nicely. And the reason for that is that the entire surface becomes a single quadratic. And it's a single quadratic mapped by the exponential x plus iy equals u plus iv to the, it's either the 2/4 or the 4/2. So there's some, there are just enough special cases that you wonder whether there ought to be something a bit better. But I suspect not. Sorry to interrupt and to hold you all up. You're ready to stop. Back to you.
Jörg, want to say something else also? I think so.
Well, originally I thought I'd give Malcolm the last word, but he already had it. So yeah, thank you. Thank you for everyone for coming. This was a wonderful get together. Malcolm and Ergen are the guilty parties, and I stood somewhat in the background. Yeah, wonderful. I hope this will be post-produced, right, Ergen?
Hopefully, I'm recording. I'm still recording. I hope everything works. I asked my wife also to record in the site. So we have 2 recording. Hopefully we have that. And then Jörg, like the Joachim Hork, like wants to turn it to a paper. He sent it like even during this chat, he sent it to me. We can all talk about it. Like Malcolm wants to turn it to a book eventually. That's another direction.
Yes,
we can all write each other. Like this is a still long journey. Like, but I think we are on the good, like good track, like for the future.
I want you to turn it into a book because I don't have enough months left.
Okay. So, okay, thanks a lot. So if you want, it has been a long day. And then tomorrow and then day after tomorrow, the conference will start 7 o'clock in California and until 1 o'clock. Like I will have another 6-hour days to like this. And then hopefully everything will work fine. Please try to come to the conference also. That would be wonderful. Like keynote speeches, etc. Like plus the lots of the papers. So see you all. Joachim is here. Do you want to talk? Like what is your idea?
Oh, I was here the whole time. I was
I didn't see you. Sorry. Like
for the
yeah.
thing. No, I just want to say that I'm really amazed by the quality and by all the reminiscences here. And I would suggest it to Ergen that on the basis of the it's possible to generate a transcript of this session, and on the basis of that to produce a seed paper. That was my suggestion, Ergun.
Actually, Joachim, I have an idea. I don't know. I can ask in front of everybody. If I have time in the December, if I turn it to this comic-like story of this whole thing, I can draw everybody.
Oh, that's such a nice idea.
Do you like it? But it will kill me, like if I try to draw them.
You don't need to draw me, but there are so many people who deserve a drawing in that gallery here.
Yeah, this will be fun, but in December I may have time. Who knows?
Get the Pixar guys to do it. They're skilled.
No, I am also a cartoonist, you know that. Like
Oh, okay.
And then, yeah, that's maybe fun because I have a software right now. We can do a cartoon stories. Like if I put everybody like within the subdivision, you can put the people together. They can discuss. So I don't know. It can kill me. I don't promise anything, but that is an idea.
Don't kill yourself, Ergen. We need you to produce so much nice events like this one. It was just fantastic.
Ergun, thank you very much. That was a fantastic session. And it's really great to see you all, Rachel, and everybody out there. Wonderful. Bye-bye.
Okay.
I wanted to say hello to Carla.
Thank you. Okay, I'm ending such that we don't have to continue. Everybody can rest. See you all. Bye-bye.
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 Thank you.